and welcome to Sleep Gravity. In the minutes ahead, you do not need to try to remember every name, every distance, or each stage in the life of a star. Let the ideas drift by slowly, much as light continues its quiet journey through space, carrying stories from distant worlds into a peaceful room here on Earth. Sunlight is probably one of the most familiar parts of life. It falls across the ground in the morning, rests along the edge of a window, warms a wall, or reflects from the surface of a glass of water. Because the sun appears each day with almost no visible change, it is easy to feel that it has always been there with the same size, the same color, and the same steady rhythm of light. Across a human lifetime, that feeling is almost entirely correct. The sun had been shining for an unimaginably long time before the first human ever looked up at it, and an equally difficult stretch of time still lies ahead before it enters the final stages of its existence. But no star keeps the same form forever. Deep beneath the bright surface we see, the sun is slowly consuming the fuel that has sustained it for billions of years. This process does not create a clock we can hear, nor does it leave any obvious difference between today and tomorrow. Only when viewed across cosmic timescales do these nearly motionless changes come together into a complete life. A star is born, remains stable through most of its existence, gradually grows older, expands, loses its outer layers, and finally leaves behind only a small, hot core at its center. We cannot wait billions of years to watch the sun pass through this entire process with our own eyes. The galaxy, however, contains countless stars born at different times. Some are younger than the sun, some are in a similar stage, and others have traveled much farther along their evolutionary paths. By observing them, we can piece together different parts of a story that no civilization could ever follow from beginning to end. About 2,500 light-years from Earth, in the region of the sky belonging to the constellation Lyra, lies a small object commonly known as the Ring Nebula. Through a sufficiently good amateur telescope, it may appear as a faint, quiet circle of light among the stars. In more detailed images, that circle becomes far more complex. Bands of gas weave through one another. Regions of material vary in density. The center seems almost empty, and a very faint star rests near the middle of the structure. The Ring Nebula is not a planet, even though it belongs to a class of objects once given the name planetary nebulae. Nor is it a place where a new star is being born. Its glowing layers of gas are the outer material of an aging star, once held close for most of the star's life, then gradually released into space as its internal structure changed. At the center of the gas lies the remaining core, far smaller than the original star, yet hot enough for its light to illuminate the star's former atmosphere from within. In that sense, the Ring Nebula is like a trace left behind after a great transformation. It does not show us exactly what the sun will look like in every detail, because no two stars are completely alike. The star that created this nebula may once have been more massive than the Sunday. The way it lost material may have been influenced by a companion star. Even the shape we see depends on the viewing angle from Earth. Still, the basic laws that produced this ring of gas also belong to the sun's distant future. One day, far beyond the future of humanity, or any civilization we can clearly imagine, the sun will no longer retain its present form. Its core will change. Its outer layers will swell, expanding through regions of space now occupied by the innermost planets. Mercury and Venus will almost certainly cease to exist as they do today. Earth's final fate is more complicated, but long before that moment arrives, our familiar world will already have become a very different place. Farther out, the giant planets and icy bodies may continue to survive, although their orbits and surrounding environments will no longer resemble the solar system we know. After its red giant phase, the sun will begin returning its outer layers to space. Material that was once part of the star will spread outward into a thin cloud. The remaining core will gradually become a white dwarf, an object roughly the size of Earth but containing the dense, hot remnants of a star that was once vastly larger. Under the right conditions, light from that core will pass through the expanding gas and create a planetary nebula that exists only briefly compared with the full lifetime of the star. So when we look at the Ring Nebula, we are not truly seeing an image sent back from the future. What appears before us is the outcome of another star with its own mass, environment, and history. Yet within those bands of gas are familiar outlines of a process the Sun will eventually undergo as well. That is why this small ring in Lyra can serve as one of the clearest windows through which we can imagine what may remain when our own star reaches the end of its life. On this journey, we will begin with the shape of the ring itself, because what seems simplest in the image conceals a complicated three-dimensional structure. From there, we will trace the story backward to the star that created it, exploring how an ordinary star becomes a red giant, why its outer layers can drift away, and what causes that gas to glow in the darkness of space. In the end, the story will return to the solar system, where the familiar planets may meet very different fates around the remaining core of the Sunday. The Ring Nebula can tell us a great deal about that future, but it also reminds us that science must always distinguish between what can be predicted with confidence and what still depends on details that are not yet fully understood. And before we can explore what the Sun will leave behind, we need to look more closely at the object serving as its distant mirror, because that glowing ring is not truly a ring at all. Text: in the summer sky of the northern hemisphere, the constellation Lyra is not especially difficult to find for those who are accustomed to looking upward. The bright star Vega stands out as a clear point of reference, while the fainter stars around it form a small shape reminiscent of the ancient lyre from mythology. Within that region of the sky, not far from two stars near the lower part of the constellation, lies an object far too small to be seen with the naked eye. Even through an amateur telescope, it does not appear as brilliant as it does in familiar astronomical photographs. Instead, it looks like a faint, slightly rounded patch, sometimes resembling a pale ring of smoke suspended against the dark sky. This is M57, the Ring Nebula, one of the best-known planetary nebula in the heavens. The distance from Earth to this object is roughly 2,500 light-years. That means the light now reaching us left the nebula long before the first telescopes were built. During all that time, its photons traveled through nearly empty space, crossing regions of sparse dust and gas within the Milky Way, until a very small fraction finally entered observing instruments on Earth. What appears through a telescope is not M57 as it exists now, but its condition thousands of years in the past. And yet, that distant past is telling the story of a stage the Sun will not enter for billions of years. A faraway object does more than allow human eyes to look backward in time. It also allows the imagination to move forward. The Ring Nebula was recorded in 1779, during an era when observing the sky still depended on lenses far smaller and less sensitive than modern instruments. Astronomers of the time often tracked comets, faint objects that could move slowly among the stars. Identifying them was not easy, because the sky contained many dim patches that looked somewhat like comets but remained fixed in the same position. It was during this kind of search and observation that the small glow in Lyra drew attention. Antoine Darquier de Pellepoix observed it while following a comet, and Charles Messier later recorded the object as well, adding it to his catalogue of stationary, fuzzy objects in the sky. Messier's catalogue was not originally created to describe the most beautiful objects in the universe. It was more like a practical set of notes for comet hunters, helping them recognize which patches of light stayed still and should not be mistaken for moving targets. M57 was the 57th entry on that list. Across generations of telescopes, an object once recorded mainly to prevent confusion gradually became one of the most important subjects for studying the old age of stars. There is something quietly revealing in this part of astronomical history. Sometimes an object is noticed not because people immediately understand its importance, but because it happens to stand in the way of a different search. The earliest instruments could not reveal the fine filaments of gas, the denser regions of material, or the faint star at the center. Observers saw only a very small disk of light, rounded and slightly blurred around the edges. Some similar objects also resembled distant planets, such as Uranus or Neptune, when viewed through the telescopes of that period. They did not look entirely like the sharp point of a star, but they were not clear enough to reveal their true nature. It was this visual resemblance that gave rise to the name planetary nebula. That name is still used today, even though astronomers have long known that planetary nebulae are not planets and are not places where planets are forming. It is one of those cases in which scientific language preserves the trace of an old misunderstanding. The term does not describe the object's origin. It simply reflects how the object once appeared through limited observing instruments. Much as a place name can preserve a story from centuries ago, the phrase planetary nebula has survived even though its original meaning is no longer accurate. A region where planets are forming usually belongs to a very young star system. In such places, dust and gas orbit a newborn star and gradually gather into larger bodies. The Ring Nebula lies near the opposite end of a star's life. It does not mark the beginning of a planetary system, but the remains of a star that has already passed through most of its existence, lost the gaseous layers that once surrounded it, and left behind only a hot core near the center. The glowing material is not fresh matter waiting to form new worlds. It is the star's former atmosphere, released from the place where it had been held for billions of years. This difference makes M57 especially relevant to the story of the Sunday. The Sun is still in a stable stage, but it belongs to the same broad class of stars that may eventually produce a planetary nebula. It is not massive enough to end in a tremendous supernova explosion. Instead, its future will unfold Uriercomus violent but no less profound rhythm. The outer layers will swell, matter will gradually escape, the hot core will be exposed, and its light will illuminate the expanding gas. The Ring Nebula shows us a version that has traveled much farther along that path, although the star that created it was not exactly like the Sun, and the final details of the two systems will not be identical. Seen from Earth, the nebula's brightest structure appears small enough to fit within a tiny ring among the stars. Yet, that apparent size is only the result of its great distance. The gas itself stretches across a region of space many times larger than the inner solar system. The gentle glow in photographs does not come from a solid surface. It is produced by extremely thin gas, where atoms are separated by distances far greater than those in the air around us. Only because we are looking through a great depth of that gas do our eyes and cameras receive enough light to reveal a distinct outline. Modern images also show that M57 does not glow in a single color. Different regions shine at different wavelengths, depending on the type of atom, the temperature, and the degree to which the gas is affected by radiation from the stellar core. The colors used in processed images help separate layers of material that the human eye would struggle to distinguish. Although the final picture may look like an object painted in bands of red, blue, and yellow, there is no solid ring in space with a clearly defined surface. There is only an expanding cloud of gas, growing thinner over time, made visible by the light of the remaining core. Text. At the center of the glowing ring lies a faint star. It is easy to overlook because the surrounding gas appears more prominent in many images, yet this small object plays the most important role of all. It is the core left behind after the original star lost its outer layers. It is far hotter than the present surface of the Sun, even though it no longer produces energy in the way an ordinary star does through most of its life. Intense radiation from the core travels into the surrounding gas, causing the atoms to glow and transforming the abandoned material into a nebula that can be observed from thousands of light years away. Even so, the familiar image of the ring still does not reveal the full structure. The dark region in the middle is not completely empty. The bright outline is not a closed strand of gas. Even the part we call the ring is simply where the light appears more concentrated along our line of sight from Earth. An observer elsewhere in the galaxy might not recognize this familiar circular shape at all. The same cloud of gas can produce a different image from a different angle, just as an object in a room may appear circular, oval, or like a narrow line depending on where we stand. For that reason, the first step toward understanding the Sun's distant future is not simply to look at the ring and search for similarities. We must first recognize that we are seeing the projection of a three-dimensional object onto a two-dimensional sky. The very feature that made M57 famous also conceals its true nature. The small ring in Lyra has never been as simple as its name suggests, because from space, it is not truly a ring at all. A ring keeps its familiar shape only when viewed almost directly face-on. Tilt it, and the circle becomes an oval. Turn it nearly perpendicular to the observer, and it may narrow into a thin line. The Ring Nebula also changes with viewing angle, but its true structure is far more complicated than a simple loop of gas tilted in space. The famous image we see in the sky is only the light of a three-dimensional object compressed onto the two-dimensional plane of an astronomical photograph. In the clearest images, the bright central region gives the impression of a closed band of gas surrounding a darker area in the middle. The outline is not perfectly circular, but it is balanced enough for the name ring to feel natural. Looking at that image alone, it is easy to imagine that the star expelled material along a single plane, creating a hollow loop like an enormous belt. Deeper observations, however, show that the glowing ring is only a denser part of a much broader structure, extending in several directions. The most prominent gas resembles a thick torus, though it is neither smooth nor perfectly symmetrical. Matter is concentrated into a broad band, thicker in some places and broken into filaments and clumps in others. Passing through the middle is a region of thinner gas that extends both toward and away from us, along our line of sight from Earth. In three-dimensional models, the full structure is often described as a combination of a thick ring and an elongated shell, somewhat like an expanded football shape, or a barrel whose two ends are not clearly closed. Earth lies close to one of the structure's axes. We are not viewing it completely from the side, nor are we looking precisely through its center. But our angle is close enough to the axis for the band of gas to appear as a closed shape. An observer elsewhere in the Milky Way, positioned farther to the side of the nebula, might see it as longer, narrower, or divided into two bright regions facing one another. A shape once regarded as an inherent feature of the object turns out to depend greatly on where the observer is standing. This is a familiar problem in astronomy. A telescope receives light arriving from a particular direction and records it on a flat detector. The front-to-back distance between layers of gas does not appear directly, as it would if someone could walk around an object in a room. One bright region may lie closer to us, while another sits trillions of kilometers behind it, yet both overlap in the image. To reconstruct depth, astronomers must look for clues beyond surface appearance. One of the most important clues comes from the motion of the gas. When material moves toward Earth, its light shifts slightly toward shorter wavelengths. When it moves away, the light shifts toward longer wavelengths. This is known as the Doppler shift, the same principle that changes the sound of a passing vehicle, although in astronomy what is measured is not the pitch of sound but the position of spectral lines. Each element in the cloud emits light at characteristic wavelengths. Astronomers separate the nebula's light into a spectrum, identify the emission lines of hydrogen, oxygen, nitrogen, and other elements, and then measure how far each line has shifted from its standard position. Some of the gas is moving toward us, while the opposite side is receding. When those velocities are combined with the location of each region in the image, the structure begins to gain depth. Areas that seem to lie on the same plane are revealed as the front and back portions of an expanding shell. This process is not like taking a complete three-dimensional photograph in a single observation. It is closer to reading many separate pieces of information and reconstructing an object that cannot be viewed directly. Images show where the light is concentrated. Spectra reveal which way the material is moving and how quickly. Computer models test whether a proposed structure can reproduce both the observed image and the measured velocities. When several kinds of data lead to the same interpretation, the three-dimensional shape becomes more reliable. The dark region inside the ring is a clear example of the difference between appearance and reality. It is not a completely empty hole passing through the nebula. The light there is weaker mainly because the gas is less dense, while its temperature and state of ionization also differ from those of the surrounding bright band. Some material still lies along that line of sight, stretching in front of and behind the central star. The human eye perceives darkness because fewer photons arrive from that region, not because the interior has been swept completely clean. Even the bright edge is not a wall of gas with a sharply defined boundary. When we look through the rim of a shell or a thick ring, our line of sight passes through a longer stretch of gas than it does near the center. More atoms lie along the same direction. Their light adds together, and the edge appears brighter and more distinct. A similar effect can be seen in a transparent soap bubble or a faint sphere, whose outer rim often stands out more clearly than the middle, because the light passes through more material. In the nebula, this effect helps transform a broad gaseous structure into a ring with a relatively well-defined outline. The three-dimensional shape also preserves evidence of how the star lost its material. If the gas had been released evenly in every direction, the remains would more closely resemble a spherical shell. The thick band, elongated lobes, and uneven regions of density suggest that the process was not as simple as a ball steadily inflating. The rate of mass loss may have changed over time. Material around the star's equator may have been denser than material near its poles. Magnetic fields, rotation, or the gravity of a companion star may also have redirected the outflow away from its original symmetry. Not every detail has a final explanation. Some structures are consistent with the influence of a faint companion star, while others may have formed through several successive phases of stellar wind. The important point is not to select a single cause too quickly, but to recognize that the nebula's shape is a record of motions that occurred before its light ever reached us. The bright band, the thinner gas, and the extended regions do more than create the beauty of the image. They preserve the story of how matter left the star and spread into space. The way humans interpret the Ring Nebula has also changed as our ability to observe it has improved. Through early telescopes, it was a small, faint disk. Better instruments revealed the darker center and the ring-like outline. High-resolution images showed that the band of gas is fragmented rather than smooth like a ribbon. Spectroscopy added the dimension of motion, while infrared observations exposed fainter components beyond the familiar bright region. Each new layer of data did not erase the image that came before. It placed that image within a larger and more complete structure. A ring keeps its familiar shape only when viewed almost directly face-on. Tilt it, and the circle becomes an oval. Turn it nearly perpendicular to the observer, and it may narrow into a thin line. The Ring Nebula also changes with viewing angle, but its true structure is far more complicated than a simple loop of gas tilted in space. The famous image we see in the sky is only the light of a three-dimensional object compressed onto the two-dimensional plane of an astronomical photograph. In the clearest images, the bright central region gives the impression of a closed band of gas surrounding a darker area in the middle. The outline is not perfectly circular, but it is balanced enough for the name ring to feel natural. Looking at that image alone, it is easy to imagine that the star expelled material along a single plane, creating a hollow loop like an enormous belt. Deeper observations, however, show that the glowing ring is only a denser part of a much broader structure, extending in several directions. The most prominent gas resembles a thick torus, though it is neither smooth nor perfectly symmetrical. Matter is concentrated into a broad band, thicker in some places and broken into filaments and clumps in others. Passing through the middle is a region of thinner gas that extends both toward and away from us along our line of sight from Earth. In three-dimensional models, the full structure is often described as a combination of a thick ring and an elongated shell, somewhat like an expanded football shape or a barrel whose two ends are not clearly closed. Earth lies close to one of the structure's axes. We are not viewing it completely from the side, nor are we looking precisely through its center, but our angle is close enough to the axis for the band of gas to appear as a closed shape. An observer elsewhere in the Milky Way, positioned farther to the side of the nebula, might see it as longer, narrower, or divided into two bright regions facing one another. A shape once regarded as an inherent feature of the object turns out to depend greatly on where the observer is standing. This is a familiar problem in astronomy. A telescope receives light arriving from a particular direction and records it on a flat detector. The front-to-back distance between layers of gas does not appear directly, as it would if someone could walk around an object in a room. One bright region may lie closer to us, while another sits trillions of kilometers behind it, yet both overlap in the image. To reconstruct depth, astronomers must look for clues beyond surface appearance. One of the most important clues comes from the motion of the gas. When material moves toward Earth, its light shifts slightly toward shorter wavelengths. When it moves away, the light shifts toward longer wavelengths. This is known as the Doppler shift, the same principle that changes the sound of a passing vehicle. Although in astronomy what is measured is not the pitch of sound but the position of spectral lines. Each element in the cloud emits light at characteristic wavelengths. Astronomers separate the nebula's light into a spectrum, identify the emission lines of hydrogen, oxygen, nitrogen, and other elements, and then measure how far each line has shifted from its standard position. Some of the gas is moving toward us, while the opposite side is receding. When those velocities are combined with the location of each region in the image, the structure begins to gain depth. Areas that seem to lie on the same plane are revealed as the front and back portions of an expanding shell. This process is not like taking a complete three-dimensional photograph in a single observation. It is closer to reading many separate pieces of information and reconstructing an object that cannot be viewed directly. Images show where the light is concentrated. Spectra reveal which way the material is moving and how quickly. Computer models test whether a proposed structure can reproduce both the observed image and the measured velocities. When several kinds of data lead to the same interpretation, the three-dimensional shape becomes more reliable. The dark region inside the ring is a clear example of the difference between appearance and reality. It is not a completely empty hole passing through the nebula. The light there is weaker mainly because the gas is less dense, while its temperature and state of ionization also differ from those of the surrounding bright band. Some material still lies along that line of sight, stretching in front of and behind the central star. The human eye perceives darkness because fewer photons arrive from that region, not because the interior has been swept completely clean. Even the bright edge is not a wall of gas with a sharply defined boundary. When we look through the rim of a shell or a thick ring, our line of sight passes through a longer stretch of gas than it does near the center. More atoms lie along the same direction. Their light adds together, and the edge appears brighter and more distinct. A similar effect can be seen in a transparent soap bubble or a faint sphere whose outer rim often stands out more clearly than the middle because the light passes through more material. In the nebula, this effect helps transform a broad gaseous structure into a ring with a relatively well-defined outline. The three-dimensional shape also preserves evidence of how the star lost its material. If the gas had been released evenly in every direction, the remains would more closely resemble a spherical shell. The thick band, elongated lobes, and uneven regions of density suggest that the process was not as simple as a ball steadily inflating. The rate of mass loss may have changed over time. Material around the star's equator may have been denser than material near its poles. Magnetic fields, rotation, or the gravity of a companion star may also have redirected the outflow away from its original symmetry. Not every detail has a final explanation. Some structures are consistent with the influence of a faint companion star, while others may have formed through several successive phases of stellar wind. The important point is not to select a single cause too quickly, but to recognize that the nebula's shape is a record of motions that occurred before its light ever reached us. The bright band, the thinner gas, and the extended regions do more than create the beauty of the image. They preserve the story of how matter left the star and spread into space. The way humans interpret the Ring Nebula has also changed as our ability to observe it has improved. Through early telescopes, it was a small faint disk. Better instruments revealed the darker center and the ring-like outline. High-resolution images showed that the band of gas is fragmented rather than smooth like a ribbon. Spectroscopy added the dimension of motion, while infrared observations exposed fainter components beyond the familiar bright region. Each new layer of data did not erase the image that came before. It placed that image within a larger and more complete structure. Text. This change reminds us that astronomical images are both windows and limitations. They allow us to see across immense distances, yet they always record an object from a single position and through a particular range of light. A beautiful photograph can make an object seem clear, while its physical nature may still require years of measurement and modeling to understand. The ring visible in the image is real in the sense that its light is reaching us, but the way that light is arranged across the sky does not reveal the complete shape of the gas. If we could close the distance and travel around the object, the view would not resemble a glowing circle suspended against a black background. Thin clouds of gas would spread across a vast region, their boundaries gradually fading as the viewing angle changed, while the central star would appear within an environment of widely varying density. The bright band that stands out from Earth might separate into overlapping layers, delicate filaments, and long regions of thinner gas. This dependence on viewing angle is one reason planetary nebulae can appear so different from one another, even when they were created by somewhat similar processes. This also places an important limit on using this object to describe the future of the Sunday. Our star may lose its outer layers and form a glowing cloud of gas, but a distant observer would not necessarily see a ring. The final shape will depend on how the material is released, how it is distributed around the star, whether outside influences are present, and the direction from which the system is viewed. The general future may be similar in its underlying mechanism, while the resulting appearance in the sky could be very different. Beneath the familiar name lies a layered, expanding structure of gas, with some material moving toward us, other regions receding, and bright areas intensified by the depth of gas along our line of sight. Astronomers cannot fly around the nebula to examine it from every side, but its light has carried enough clues for them to reconstruct the space it occupies. The ring gradually becomes a complex shell, while the darkness at its center is recognized as a region of thinner gas rather than absolute emptiness. As the true shape begins to emerge, the focus shifts from appearance to the physical nature of the object itself. Each glowing region contains different elements, moves at a different velocity, and responds to radiation in its own way. To read the history of the star that created this structure, astronomers must do more than take photographs. They must separate the light into smaller signals, because within those narrow spectral lines, the gas begins to reveal what it is made of, how it is moving, and when it left the star. Text. The Ring Nebula is far too distant for any present-day spacecraft to reach within a useful span of time. We cannot collect samples of its gas, place instruments among its layers of material, or observe the structure from several different locations. Nearly everything we know comes from the tiny amount of light that has crossed thousands of light years before reaching the mirrors of telescopes. Those photons do more than create a beautiful image. They carry traces of chemical composition, temperature, density, motion, and even regions of matter invisible to the human eye. The light familiar to us is only a small part of the entire electromagnetic spectrum. Human vision detects a relatively narrow range of wavelengths, from violet to red, while the universe also emits ultraviolet light, infrared radiation, radio waves, X-rays, and many other forms of radiation. Each range of wavelengths interacts with matter in its own way. A layer of gas that stands out in visible light may appear faint in the infrared, while a region of dust that nearly disappears from human sight can become clear when observed with instruments sensitive to heat. Studying a nebula, then, is not simply a matter of photographing the same scene with a larger camera. It is more like opening several windows, each revealing a different part of the same structure. Through a small telescope, the object in Lyra usually appears as little more than a pale gray smudge. The human eye cannot gather enough light to detect the rich colors seen in long-exposure photographs. Astronomical cameras can collect photons for many minutes or even hours, bringing out regions too faint for the retina to perceive in a single glance. As the exposure time increases, the outline becomes clearer, the center reveals more detail, and the faint gas surrounding the main ring begins to emerge. Even a deep exposure image only shows where light is concentrated. To understand what kind of matter is producing that light, astronomers use filters designed to admit only very narrow ranges of wavelengths. One filter may highlight light emitted by hydrogen, another may be sensitive to oxygen atoms that have lost 2 electrons, while another records nitrogen in cooler or denser regions. When the separate images are compared, the nebula no longer appears as a uniform cloud of light. It becomes divided into regions with different physical conditions. The names of the elements can sometimes make these images seem like complete chemical maps, but the reality is more subtle. The strength of an element's glow does not depend only on how much of that element is present. It also depends on the temperature of the gas, the energy of the radiation from the central star, and how many electrons have been removed from the atoms. The same material may glow brightly in one region and more weakly in another, even when the amount of the element has not changed significantly. Researchers must combine several emission lines with physical models before drawing conclusions about the composition or conditions within the nebula. Spectroscopy extends this ability far beyond what a filtered image can provide. When light is separated into its individual wavelengths, bright lines appear at characteristic positions, like the signatures of particular atoms and ions. The location of each line identifies the material producing the light. Comparisons between the strengths of several lines help estimate temperature and density, while shifts in their positions reveal the direction of motion. A narrow band of light can contain more information than the entire visible appearance of the object in an image, even though the spectrum itself may look like nothing more than thin colored lines against a dark background. Most of the nebula's glowing shell is made of hydrogen and helium, the 2 most abundant elements in the universe. Traces of oxygen, nitrogen, carbon, and other elements reveal more about the material that once existed inside the star. Some of it was inherited from the cloud of gas in which the star formed. Other material underwent changes deep within the star during its long lifetime before being carried outward in its final stages. The expanding cloud does not merely show what the star has lost. It also preserves clues to processes that occurred far below its surface, in regions no telescope could ever observe directly. Visible light provided many of the most familiar images of the Ring Nebula. The Hubble Space Telescope, operating above Earth's atmosphere, can record fine details that are often blurred by turbulence in the air. Its observations revealed that the bright band is not continuous, but is made up of numerous filaments, knots of material, and interspersed dark regions. The large-scale structure was already uneven, and as the resolution improved, complexity appeared on smaller scales as well. Earth's atmosphere protects life, but it also absorbs or distorts some of the light arriving from space. Telescopes positioned above the atmosphere avoid many of these limitations. They can observe wavelength ranges that only partly reach the ground, while also maintaining more stable images over long periods. This is one reason space observatories can transform our understanding of objects that have been known for centuries. The nebula does not suddenly change because a new telescope turns toward it. What changes is the amount of information the instrument is able to collect. Infrared light adds another layer of vision, It has wavelengths longer than the red light visible to the human eye. Some infrared radiation can pass through dust more easily than visible light, while also revealing molecules and warm grains of dust. In the Ring Nebula, infrared observations bring out delicate structures within the main band, cooler regions of material, and extremely faint components beyond the area that usually dominates optical images. The James Webb Space Telescope carries several infrared instruments, but two are especially useful for observing this object. Its near-infrared camera records wavelengths just beyond the limits of human vision, where fine filaments and narrow boundaries within the glowing band become clearly visible. Its mid-infrared instrument can detect cooler material and faint structures farther from the central star. The two images are not simply brighter and darker versions of the same scene. Each emphasizes different physical components. Webb's observations reveal that the familiar glowing region is organized far more intricately than its soft appearance in older images would suggest. Fine filaments weave through one another, denser pockets of gas lie between thinner regions, and the outer parts of the nebula contain extremely faint traces that were previously difficult to detect. These details will become important as the story moves deeper into the way the star lost its material. For now, they demonstrate a fundamental principle. Higher resolution does more than make an image more beautiful. It changes the scientific questions that can be asked. A structure that once appeared to be a continuous band of gas may turn out to consist of countless smaller regions. A faint halo, once dismissed as background noise, may preserve evidence of earlier episodes of mass loss. A dark area may not be lacking in matter at all, but may instead contain material that does not emit strongly within the wavelength range being observed. Each time the filter or instrument changes, the interpretation must be reconsidered, because absence from an image does not mean emptiness in space. The colors in astronomical images must be understood in the same spirit. If someone could travel close enough to the nebula and look at it with the naked eye, the view would not necessarily resemble the vivid colors displayed on a screen. The gas is extremely thin, its surface brightness is very low, and human vision in darkness is far less sensitive to color than a camera collecting light over a long exposure. Image processors often assign colors to different filters so that separate components can be distinguished or changes in physical conditions can be emphasized. Blue may represent one region of emission and red another, even when the original wavelengths lie beyond the range of human sight. This does not make the image artificial. The underlying data still comes from real light recorded by the telescope. Color serves as a visual language, translating differences that are difficult to see into regions that can be clearly distinguished. Just as a weather map uses color to represent temperature or rainfall, astronomical images use it to reveal features the human eye could not recognize on its own. Visual beauty and scientific value do not exclude one another. Both can arise from the same set of data, as long as the method of presentation is properly understood. The combination of imaging, spectroscopy, and observations across multiple wavelengths transforms the cloud of gas into a kind of record. Images show how the structure is distributed across the sky. Spectra reveal composition and motion. Infrared observations bring out cooler material, dust, and extremely faint layers. Data gathered over time can also be used to measure the nebula's expansion, although the change over only a few years is so small that it can be detected only through highly precise measurements. No single method can tell the entire story, but the different pieces can test one another and gradually narrow the range of explanations that are likely to be correct. Throughout the history of observation, each generation of instruments has added another layer to that record. At first, there was only the position of a faint patch among the stars. Then came its ring-like shape, followed by the detection of the central star, the different emission regions, the motion of the shell, and the infrared structures along the outer edge. New data has not made the object more unfamiliar. It has brought it closer to human understanding by turning light into measurements that can be compared. The same approach is used to study the Sunday. Although it is extremely close compared with other stars, its deep interior still cannot be seen directly by the eye or by a camera. Scientists interpret its light, surface oscillations, and streams of particles to infer what is happening inside. In the case of the star that created the Ring Nebula, only the core and the released layers of gas remain, but the principle is much the same. What cannot be touched is studied through the traces it sends outward. When those traces are brought together, the cloud becomes more than the remains of an aging star. It becomes evidence of the core's temperature, the rate of expansion, the composition of the material, and the different phases during which gas was lost. To understand how a star could leave behind such a record, the story must return to a time long before the ring appeared, when that star was still shining steadily and was not so different from the sun illuminating Earth today. Text. Long before the layers of gas in the Ring Nebula drifted into space, the star at its center lived in an almost ordinary state. There was no glowing ring, no exposed stellar core, and none of the delicate filaments now observed by modern telescopes. For most of its life, it was probably simply a stable star among countless others in the Milky Way, shining continuously for billions of years without revealing any obvious sign of the ending waiting far ahead. The sun is currently passing through that same period of life. Each morning, the light reaching Earth arrives with such regularity that the activity of the star itself is almost taken for granted. We notice clouds moving, seasons changing, and weather shifting, while the source of light at the center of the solar system seems to remain the same. Across the timescale of a human life, that impression is largely accurate. The sun's brightness varies slightly, and its surface is always in motion, but its overall structure has remained stable for a span of time longer than the entire history of civilization. That stability does not mean the interior of the star is quiet. The center of the sun is an environment of extremely high temperature and pressure, where matter is compressed beneath the weight of all the layers above it. Under these conditions, hydrogen nuclei can move close enough to overcome the electrical repulsion between them and take part in nuclear fusion. Through a sequence of several steps, 4 hydrogen nuclei ultimately form one helium nucleus. The resulting helium has slightly less mass than the original particles combined, and the difference is released as energy. This is not burning in the same sense as a flame on Earth. Ordinary fire depends on chemical reactions between atoms, usually involving oxygen, while fusion changes the nuclei of the atoms themselves. The sun's energy does not come from coal, gas, or a store of fuel burning in space. It comes from matter being rearranged in the core under conditions that can be reproduced on Earth only briefly and on a very small scale. The most common reaction in the sun is known as the proton-proton chain. The name may sound technical, but the basic idea is relatively simple: hydrogen nuclei, which are single protons, combine step by step to form helium. Each individual reaction releases only a tiny amount of energy, yet so many reactions occur simultaneously in the core that their combined output is enough to keep the sun shining continuously and provide nearly all the natural energy received by Earth's surface. The energy created in the core does not travel directly outward at once. Deep inside the star, light is repeatedly absorbed and re-emitted by the surrounding matter. With every interaction, its direction changes. A photon may take an extraordinarily long time to escape the interior, even though once it leaves the surface, sunlight needs only a little more than 8 minutes to reach Earth. Energy produced at the center in the distant past may only now be emerging from the surface as the light we see today. Not every product of these reactions remains trapped for so long. Particles known as neutrinos interact so weakly with matter that they leave the core almost immediately and pass through the rest of the sunday. Trillions of solar neutrinos move through every person's body each second without creating any sensation. Detecting them on Earth has provided some of the most direct evidence that nuclear fusion is truly taking place deep inside the star. While nuclear reactions provide energy, gravity continuously pulls all the sun's material toward the center. If gravity acted alone, the sun would contract. If only the pressure of hot gas and radiation were present, the layers of matter would tend to expand. The star's long-lasting structure exists between these opposing tendencies. Gravity compresses matter inward, while internal pressure resists that compression. This balance is known as hydrostatic equilibrium, even though the star itself is never completely motionless. The sun vibrates, rotates, generates magnetic fields, and constantly moves hot material through its outer layers. Sunspots appear and disappear. Loops of plasma rise above the surface. The solar wind carries charged particles throughout the planetary system. Beneath its stable appearance lies an active star, but all of these variations occur within an overall structure that remains intact. It is like an ocean filled with waves, currents, and tides, while the body of water as a whole remains within its familiar boundaries. Astronomers call this state the main sequence phase. The term comes from the way stars are arranged on a diagram that compares brightness with surface temperature. When thousands of stars are placed on this diagram, most fall along a clearly defined band. Stars in this region are fusing hydrogen in their cores and maintaining a long-term balance. The Sun occupies no exceptional position on this band. In terms of mass, temperature, and brightness, it is a relatively ordinary star. That very ordinariness makes the Sun a useful point of reference. It does not belong to the class of massive stars that live quickly and end in enormous explosions. Nor is it a small, faint red dwarf capable of remaining active for far longer than the present age of the universe. With a mass between those extremes, the Sun spends roughly 10 billion years in the main sequence phase. It has now completed nearly half of that time. During the approximately 4.6 billion years since it formed, the Sun has converted some of the hydrogen in its core into helium. Most of the hydrogen in the star as a whole remains unchanged, but not all of it can be carried into the central region where fusion can continue. The star's lifetime is determined not only by its total amount of hydrogen, but by how much fuel lies within the region where the temperature and pressure are high enough. As the chemical composition of the core changes, its density, temperature, and the way energy travels outward change as well. Even during what is called its stable phase, the Sun does not remain completely unchanged. As helium gradually accumulates in the core, the star slowly grows brighter. Models show that the young Sun was significantly dimmer than it is today. The increase in brightness is so gradual that it cannot be noticed across a few generations, but over hundreds of millions of years, its effects on the planets can become substantial. Earth's climate history, the long-term presence of liquid water, and the distant future of the biosphere are all connected to this subtle but continuous change. This clarifies a point often overlooked when we say that the Sun has about 5 billion years remaining before it enters the red giant phase. Earth will not necessarily preserve its present environment until that time. As the Sun continues to brighten, the amount of heat reaching the planet will also increase. In the distant future, the systems that regulate the climate will no longer be able to keep temperatures within the range they occupy today. The oceans and atmosphere may change profoundly long before the Sun's surface expands anywhere near Earth's orbit. Even so, these changes unfold far too slowly to pose a danger within the human era. Hundreds of millions or billions of years are not simply an extension of recorded history. They represent spans of time many times longer than the entire existence of our species. Long enough for continents to shift position, species to appear and disappear, and the planet's surface to be remade again and again. In the story of the Sun's old age, time is more than a large number. It is the distance between two states of a planetary system so different that they can scarcely be compared directly. The long stable lifetime of a star also explains why a planetary nebula is so rare in terms of time. A star may fuse hydrogen in its core for billions of years, while the glowing gas at the end of its life remains clearly visible for only tens of thousands of years. If the entire main sequence lifetime were compressed into a single day, the nebula would appear near the very end as a brief moment before the light of the gas slowly faded. Telescopes can observe this stage because the Milky Way contains an immense number of stars, each one passing through a different point in its life. The Ring Nebula is the result of a short transitional period, but behind it lies a long age of stability much like the one the Sun is experiencing now. The former star once held its gaseous layers close, possessed a core that converted hydrogen into helium, and remained balanced between gravity and internal pressure. The atoms now scattered throughout the glowing ring spent far longer inside the star than they have spent drifting freely through space. From Earth, the Sun's stability provides the underlying rhythm for nearly every activity of life. Plants receive energy from its light, the atmosphere moves heat between regions, and the oceans store and distribute warmth through vast currents. That energy appears continuous, yet it begins with reactions occurring in a region that occupies only a small part of the star's interior. The distance between the Sun's core and a leaf on Earth connects many layers of physics, from nuclear fusion to light, climate, and biology. Human beings themselves arose during this stable interval. Not only civilization, but the entire history of complex life has depended on the Sun remaining sufficiently steady for an extremely long time. If the star changed as rapidly as a massive star, biological evolution on Earth might not have had enough time to produce the forms of life that exist today. The Sun's ordinariness, on an astronomical scale, created a quiet interval long enough for a small planet to develop oceans, an atmosphere, and living beings capable of observing the very star that sustained them. But balance does not mean permanence. With every passing second, some of the hydrogen in the core is converted into helium. The change at any single moment is far too small to alter the Sun before our eyes, but over billions of years, those differences accumulate into a new structure. The core becomes richer in helium, its temperature rises, the region of active fusion shifts, and the balance that once kept the star stable must adjust. A star does not suddenly recognize that its fuel is running low and then move into another state. The process is continuous and so gradual that there is no single day that could be called the moment when the Sun leaves its adulthood behind. The inner layers respond to changes in composition. The core contracts little by little, and the outer regions adjust to the new flow of energy. Only when viewed across a sufficiently long timescale do we divide a star's life into distinct stages with separate names. Most of the history of the star that created the Ring Nebula also passed within this almost unremarkable stability. The ring of gas is the part that can be seen most easily today, while the billions of years that came before left no similarly striking shape. Yet it was that long and ordinary lifetime that prepared everything that followed. Helium accumulated in the core, the internal structure changed, elements were redistributed, and the star's source of energy gradually shifted toward a different mode of operation. When the hydrogen at the very center is no longer sufficient to sustain fusion at its former rate, gravity begins to gain the advantage in the deepest part of the star. The core contracts and grows hotter, while hydrogen in a surrounding shell continues to fuse more intensely. The change begins within a very small region, but its effects spread through the entire star, causing the outer layers to expand to a size they had never reached before. This is a transition the Sun has not yet entered, but the star of the Ring Nebula left it behind long ago. After billions of years of appearing almost unchanged, the old balance began to give way to a new structure, one in which the center contracted while the rest of the star slowly swelled outward. For most of its life, a star maintains its stable appearance because hydrogen is continuously fused into helium in the core. Yet that same stability also creates the conditions for the next stage. Each reaction leaves more helium at the center, while the amount of hydrogen available for fusion there gradually declines. The star as a whole still contains a great deal of hydrogen throughout its vast outer layers, but most of that material lies where the temperature and pressure are not yet high enough for fusion to proceed efficiently. What matters is not that the star has used every trace of hydrogen, but that the central region once responsible for most of its energy has changed in composition. The helium accumulating in the core cannot immediately begin to fuse. For helium nuclei to combine, the environment must become significantly hotter than the conditions required for hydrogen fusion. At this stage, the core has not yet reached that temperature, so the newly formed helium contributes almost nothing to energy production. The center of the star becomes an increasingly dense mass of material, bearing the weight of the layers above, while no longer receiving the same support from strong fusion reactions. As the pressure produced by nuclear reactions in the central region decreases, gravity causes the core to contract. This contraction is not like an object falling freely or collapsing all at once. The star adjusts step by step through a process that may last hundreds of millions of years. Matter in the core is pressed closer together, its density rises, and gravitational energy is converted into heat. The center becomes smaller while also growing hotter, a combination that may seem contrary to the way familiar objects usually change on Earth. Heat from the contracting core spreads into the layer of hydrogen immediately surrounding it. Before this point, that region was not hot enough to play a major role in energy production. As its temperature rises, the hydrogen there begins to fuse more intensely, forming a shell of nuclear reactions around the nearly inactive helium core. Instead of a broad energy-producing region at the center, the star now has a dense inner core surrounded by a shell where fusion is taking place. This change in the location of energy production forces the entire outer structure to adjust. The hydrogen-burning shell may release energy at a greater rate than before. That energy travels outward, heating the layers of gas above and causing them to expand. The star begins to leave behind its familiar size, first passing through a transitional stage and then swelling more dramatically. The expansion is not caused by the core growing larger. The center is still contracting. It is the outer gas that moves farther away, even though the origin of the change lies deep within a much smaller region. This is one of the most striking patterns in stellar evolution. The interior contracts while the exterior expands, the core grows hotter while the surface becomes cooler, and the star grows brighter even as the temperature of its outermost layers falls. These seemingly opposing changes all arise from the way energy is produced and transported after hydrogen fusion at the center can no longer continue as it once did. As the outer gas expands, the same flow of energy must pass through a much larger surface area. The visible surface of the star, known as the photosphere, becomes cooler than it was during the main sequence phase. This lower temperature shifts its color gradually toward orange and red, although anyone close to such a star would still receive far too much light to look at it directly. From a distance, the combination of enormous size and a cooler surface creates the appearance of a red giant. The word red may suggest that the star is fading, like an ember cooling after a fire. In reality, red giants often release far more total energy than they did while on the main sequence. Their surfaces are cooler per unit area, but their overall surface area has increased enormously. A star can become redder, cooler in its outer layers, and still shine much more brightly when its total energy output is considered. The star also does not have a solid surface expanding like a sphere of dense material. The photosphere is simply the layer from which most of the light finally escapes. Both below and above it are gas and plasma, whose density changes continuously. As an aging star expands, the visible boundary moves outward, while the outer layers become thinner and less tightly held by gravity. These conditions will become important later, when matter begins, leaving the star at an increasing rate. The transition into a red giant does not occur in a single step. At first, the star passes through the subgiant phase, when its brightness and size gradually increase, but its final form has not yet emerged. The helium core continues to contract, the hydrogen shell around it continues producing energy, and the outer envelope expands at a pace that is slow compared with a human life, but relatively fast within the lifetime of a star. After billions of years of near stability, only a small fraction of the remaining time is needed for the star's size to change dramatically. In the case of the Sun, this expansion will unfold over hundreds of millions of years rather than in a single moment that could be observed like an explosion. There will be no one day when the star suddenly changes from its present state into an enormous red sphere. Each stage flows continuously into the next through gradual adjustments in temperature, density, and energy transport. Only with a clock capable of running for millions of years would we see the glowing surface slowly moving outward and the innermost orbits becoming increasingly immersed in a hotter environment. During this period, the helium core continues to gain material. Hydrogen in the surrounding shell fuses into helium, and that newly formed helium is added to the center. The mass of the core gradually increases, gravity compresses it more strongly, and its temperature continues to rise. Eventually, when the conditions become hot enough, helium can begin fusing into carbon and oxygen. But before that transition occurs, the star has already expanded far beyond its original size and become an object entirely different from the familiar sun we see today. Helium fusion does not last nearly as long as the hydrogen burning phase. The new source of energy may temporarily cause the star to contract and become more stable, but further changes appear as the helium in the core begins to decline. The later life of a star consists of several episodes of adjustment, contraction, and expansion, rather than a straight path moving in only one direction. For this story, the most important point is that the star begins to lose the long-term stability that once kept its gaseous layers at familiar distances. The star that created the Ring Nebula passed through similar stages, although its original mass and the details of its evolution may have differed from those of the Sunday. The evidence of that process no longer appears as a red giant, because the outer layers departed long ago. They now exist in the glowing cloud, while the small core at the center is the final result of profound changes that occurred deep within the star. By observing the present structure, astronomers are seeing the later part of the story, while models of stellar evolution allow them to trace it backward to the time when the core contracted and the outer gas began to expand. Our understanding of this stage does not come from following a single star for billions of years. The Milky Way contains stars of many different ages and masses. Some remain stable like the Sun, some are leaving the main sequence, some have become red giants, and others have already lost their outer layers and formed nebulae. When their positions are plotted on a diagram of temperature and brightness, a sequence of evolution begins to emerge. Physical models are then used to test whether changes within the core can produce the characteristics that astronomers actually observe. Text: as the Sun leaves its stable state and expands into a red giant, the greatest change will not be limited to the size of the star itself. The entire region around it will be divided into zones with conditions very different from those of today. The innermost planets will face the advancing outer layers of the Sun. Earth will be affected by an increasingly powerful source of light, and the icy worlds at the farthest reaches may receive levels of heat they have not experienced since the solar system first formed. Today, Mercury orbits closer to the Sun than any other planet. Its surface already experiences enormous differences in temperature between day and night, because the planet has almost no atmosphere thick enough to redistribute heat. As the Sun grows brighter and begins to swell, the space between the stellar surface and Mercury's orbit will gradually narrow. Even before the outer gas reaches the planet, the increasing heat will be enough to raise surface temperatures dramatically, causing rock to vaporize and creating an environment in which matter can scarcely remain in the familiar solid state. By the time the red giant phase is fully developed, Mercury will almost certainly lie within the Sun's expanded atmosphere. A small planet cannot maintain the same orbit while moving through the star's thin but immense outer gas. Drag will gradually drain its orbital energy, while tidal interactions pull it closer to the center. The final result will not resemble a rocky sphere being swallowed by flame in a single instant. Its orbit will decay, its material will be heated, its surface will evaporate, and what remains will blend into the star's outer layers through a process far more prolonged than dramatic images often suggest. Venus lies farther away, but that distance will not be enough to protect it during the sun's greatest expansion. Even today, its thick atmosphere, composed mostly of carbon dioxide, makes the surface of Venus hotter than Mercury, despite its greater distance from the Sun. In the distant future, the additional heat will drive its atmosphere and surface into even more extreme conditions. Models of stellar evolution generally indicate that the Sun's outer layers may expand beyond the orbit of Venus, leaving the planet almost no chance of surviving intact. The two innermost worlds present relatively clear cases. Earth is more complicated, not because the planet can resist the Sun's evolution, but because its orbit lies near a region where several effects compete. As the star loses mass through stellar winds, its gravitational pull weakens, causing planetary orbits to expand outward. At the same time, the Sun is swelling, while tidal forces may remove energy from Earth's orbit and draw the planet inward. Whether Earth escapes the stellar surface or is eventually pulled into it depends on the relative strength of these processes. There is no similar uncertainty about the survival of life as we know it. Long before the red giant phase begins, the Sun's increasing brightness will have altered Earth's environment profoundly. The oceans may gradually evaporate, water vapor in the atmosphere may be broken apart, and hydrogen may escape into space. The carbon cycle that once helped stabilize the climate will no longer function in its familiar way, and the surface will become too hot for present-day ecosystems. Whether Earth ultimately survives as a rocky body does not change the fact that the blue world of oceans, clouds, and complex life will have disappeared long before then. In models where the planet avoids the Sun's outermost layers, it will still pass through an era when the sky is dominated by an enormous red star. As the Sun's radius grows to hundreds of times its present size, its visible surface will cover a vast portion of the sky. Its light will no longer have the familiar yellow-white color, but the total energy reaching Earth's orbital region will still far exceed what the planet can endure. The surface may then consist of heated rock, molten material, and a secondary atmosphere formed from substances released by the crust. The Sun's expansion will not stop at one fixed radius. During different stages of its old age, the star may contract somewhat and then expand again, depending on the nuclear reactions occurring in the core and in the surrounding shells. The greatest peaks of expansion will be the decisive moments for the nearby planets. An orbit may remain outside the star's atmosphere for most of this period and still be overtaken during a shorter phase when the stellar radius reaches its maximum. Mars lies farther out and will probably avoid being directly engulfed by the Sun's visible surface. But surviving in orbit does not mean the planet will remain unchanged. Its thin atmosphere will be exposed to far more intense radiation, water ice, and carbon dioxide. In the soil and polar caps may sublimate, and the surface will become significantly warmer. For a time, regions once far too cold may reach higher temperatures, but this change will occur within a system moving toward instability, not as the lasting revival of a habitable world. Descriptions of the future Mars can sometimes create the impression that the red planet might become a second Earth as the region receiving suitable warmth moves outward. In reality, temperature is only one of many conditions required for a stable environment. Mars has low gravity, a thin atmosphere, no remaining global magnetic field, and far less accessible water than Earth. A warmer period could alter the surface, release gases, and allow localized liquid water to exist for a time, but it would not automatically create deep oceans or a lasting atmosphere. Farther out, Jupiter and Saturn will almost certainly remain beyond the surface of the red giant Sunday. The two gas giants have no solid surfaces to be heated in the same way as Earth or Mars. The additional warmth will mainly affect their upper atmospheres, changing their temperatures, clouds, and chemistry. Compared with the internal energy the giant planets still release from within, the Sun's new output will shift their energy balance, but it will not transform them into entirely different objects in a single step. The moons around Jupiter and Saturn present a more varied story. Europa, Ganymede, Callisto, Enceladus, and many other satellites contain large amounts of water ice, some of which may cover oceans buried deep beneath their surfaces. As the sun grows brighter, the surface ice will receive more heat. At certain times, regions that were once completely frozen may begin to melt or develop temporary atmospheres made of water vapor and other volatile substances. This warming will not take place within a calm and lasting environment like the one Earth experiences today. The brightness of the red giant will continue to change, stellar winds will become stronger, and high-energy radiation will affect any newly formed thin atmospheres. An icy moon may pass through a favorable temperature range for a brief period on astronomical timescales, then continue warming or begin cooling again as the star moves into another stage. The habitable zone, meaning the range of distances where temperatures might allow liquid water on the surface under suitable conditions, will move steadily outward rather than remaining fixed around any particular orbit. Titan, Saturn's largest moon, is an especially interesting case. Today, its surface is too cold for water to remain liquid, while methane and ethane can form clouds, rain, rivers, and lakes. Under the stronger light of the aging sun, methane on the surface and in the atmosphere will change more rapidly, while water ice may begin to play a different role. For a time, Titan could become a much warmer environment, but its chemistry and climate would still differ profoundly from those of Earth. Uranus and Neptune lie at even greater distances. When the sun becomes a red giant, it will appear much brighter in the skies of these two planets, though still smaller than it would from the inner orbits. Temperatures in their upper atmospheres will rise, cloud layers and chemical reactions may change, and their icy moons will receive a new source of energy. Worlds now almost locked in deep cold may enter a transitional period in which volatile substances begin moving more actively between the surface and the atmosphere. Beyond Neptune lies the Kuiper Belt, home to Pluto, and many smaller icy bodies. Under the sun's present light, much of their surfaces remains at extremely low temperatures, allowing nitrogen, methane, and carbon monoxide to freeze. As the central star grows brighter, these ices will sublimate and create thicker atmospheres for a time. Surfaces that were once nearly motionless may develop winds, haze, flowing material, and stronger seasonal cycles. Some models suggest that the region warm enough for liquid water could move outward toward the giant planets or even beyond them during the red giant phase. This is sometimes described as a final opportunity for icy worlds, but that idea must be kept within careful limits. Suitable temperatures do not guarantee that life will appear, especially when stable conditions may last only briefly. The chemistry may be very different, and radiation from the aging star may vary strongly. Science can only say that some places will become warmer and may support liquid water under certain conditions. It cannot turn that possibility into an ecosystem. While the expanding light affects each region, the sun will also be losing material continuously. Stellar winds during the red giant phase will be far denser than they are today, carrying gas and dust through the planetary system. Planets with magnetic fields or thick atmospheres will interact with this flow in their own ways, while smaller bodies will more easily lose any newly formed gaseous layers. The boundary created by the solar wind around the entire system will also change, making interplanetary space very different from its present state. The loss of mass will also cause all planetary orbits to widen. If material leaves the star slowly compared with the orbital periods of the planets, their paths will adjust gradually rather than being disrupted all at once. Distant planets may move outward while continuing to orbit the Sunday. The final arrangement of the planetary system after this stage will depend on how much mass is lost, how quickly it escapes, and the gravitational interactions among the bodies that remain. When the red giant reaches its greatest size, the solar system will no longer have a simple dividing line between worlds that survive and worlds that disappear. Mercury and Venus will almost certainly no longer remain intact. Earth lies in a region where the outcome depends on several competing processes, but its life-supporting environment will have vanished long before. Mars may survive as a heated, rocky world. The giant planets will continue orbiting the star, while many moons and icy bodies pass through warmer intervals within a system changing rapidly on astronomical timescales. What is striking is not only how large the Sun will become, but how the same transformation will produce opposite results at different distances. Near the center, heat and expanding gas will destroy rocky worlds. Farther away, the additional energy may release layers of ice that have remained still for billions of years. In the outermost regions, small bodies may develop atmospheres or surface activity, while the planets that once orbited close to the Sun have already lost their former shapes. No observer on Earth today will ever face that sky. The span of time is so vast that even the shapes of the constellations will have changed completely, while the Milky Way continues through many rotations. The value of looking into this distant future does not lie in preparing for an approaching event, but in understanding that the solar system is also a structure with a history, born in the past and destined to keep changing long after the human era. The star that created the Ring Nebula must have passed through a similar period. If planets once orbited it, the nearest worlds may have been destroyed, while more distant ones would have adjusted their orbits and environments as the star changed. We cannot clearly see that entire former planetary system, but the glowing gas tells us that the central star expanded, lost material, and left behind the stable state that had lasted for billions of years. After reaching its enormous size, the Sun will not hold its outer layers at those distances forever. The gas will become thinner, gravity will weaken in the outer regions, and changes within the star will drive increasingly powerful outflows of matter. The atmosphere that once extended across the inner orbits will begin to separate from the star, carrying material into space and gradually revealing the hot core within. This will not occur as a single explosion. The star will release its gaseous layers through several stages, with each episode leaving a different trace in the surrounding space. From those layers of material, a planetary nebula may form, and the ring now observed in the constellation Lyra is the still glowing result of a process the Sun has not yet begun. In the final stages of its life, a star like the Sun begins to lose stability in its outer layers of gas. Its radius has already grown enormously. The density in the outer regions has fallen, and gravity there is much weaker than it is near the core. Material in the highest layers is still held by the star's attraction, but only a relatively small amount of additional energy is needed to carry it farther outward, where the chance of returning becomes increasingly small. The immense atmosphere begins to form a transitional region, no longer belonging entirely to the star, yet not fully separated into space. The loss of material does not begin at a sharply defined boundary. Even the Sun today continuously releases charged particles through the solar wind, although the amount of mass it loses is extremely small compared with the star's total mass. As it enters the red giant phase and then moves into later stages of old age, that outflow can become far stronger. The escaping gas no longer takes the form mainly of a thin, fast stream of particles like the one we see today. Instead, it becomes a denser, slower flow carrying atoms, molecules, and newly formed grains of dust. One important cause lies in the star's own rhythm of activity. The outer layers may contract and expand in cycles lasting months or years. Each time the star swells, material near the surface is lifted to greater heights. As that gas cools while moving outward, some of it may not fall all the way back before the next expansion begins. Over many cycles, the outer layers are raised farther and farther away, making it easier for stellar winds to carry them beyond the region where gravity is strongest. These pulsations are not like a solid surface rising and falling in a smooth, regular motion. A star is an enormous body of gas and plasma, in which temperature, density, and movement change with depth. Some regions may expand more strongly than others. Vast convection cells carry hot material upward from the interior, and cooler gas sinks downward. In a red giant, a single convection cell can be wider than the entire distance between Earth and the Sunday. The visible surface is no longer smooth or evenly balanced, but is constantly reshaped by flows of matter on a scale unlike anything found in the atmosphere of a planet. Once the gas has been lifted far enough from the hotter regions, the temperature falls enough for some atoms to bond together and form tiny grains of dust. Depending on the star's chemical composition, these grains may contain carbon or minerals rich in silicon and oxygen. They are not dust in the everyday sense of soil fragments or fibers in a room, but small, solid particles that condense directly from gas, sometimes beginning with only a relatively small number of atoms. Dust plays a role far greater than its size would suggest. The solid grains absorb and scatter starlight, receive momentum from the radiation, and then transfer that motion to the surrounding gas through collisions. Light, often thought of as something with almost no weight, can still exert a very small pressure. On Earth, this effect is difficult to notice in daily life. Around a highly luminous giant star, however, its accumulated influence on countless dust grains can help push an entire flow of material outward. Pulsations lift the gas, lower temperatures allow dust to form, and radiation pressure helps carry both dust and gas farther away. These three processes are not always separate, but continually reinforce one another within a changing environment. The stellar wind grows denser and creates an expanding envelope around the star. Escaping material may travel at only a few tens of kilometers per second, slow compared with many high-energy events in the universe, yet fast enough to cross immense distances when the process continues for thousands or tens of thousands of years. The outflow also does not necessarily occur evenly in every direction. Rotation may cause matter to be distributed differently around the equator and the poles. Magnetic fields may guide the gas along preferred paths. If the system contains a companion star, its gravity can pull, compress, or twist the material into asymmetrical structures. Even around a single star, enormous convection cells and uneven pulsations may produce layers of gas that bulge outward in some places and vary greatly in thickness. This is when the earliest outline of the future nebula begins to appear, long before the cloud becomes clearly luminous. A dense flow of material around the equatorial region can make later outflows escape more easily in two polar directions, creating an elongated structure. Repeated episodes of mass loss may leave behind several nested shells. If the rhythm of the outflow is influenced by a companion object, the relatively regular spacing between those layers may preserve the orbital period of the system. The final visible shape is not created in a single moment. It is the accumulated result of many motions that occurred while the star was still deeply enclosed within its own thick atmosphere. In the later stages of old age, the star's core undergoes its own sequence of changes. After the helium at the center begins to run low, the core, now composed mainly of carbon and oxygen, continues to contract while nuclear reactions take place in thin surrounding shells. One shell may fuse helium, while another farther out fuses hydrogen. These two sources of energy do not always operate at a steady intensity. The helium-burning shell can undergo powerful surges, known as thermal pulses, causing the star's structure to readjust and altering the rate at which it loses material. The term thermal pulse may suggest a sudden explosion, but on the scale of a star, it is an internal disturbance that unfolds over a period far longer than anything in human experience. Energy from the helium shell rises, the star expands, other burning layers temporarily change, and the structure gradually settles again. Such episodes may repeat, each one helping to mix material inside the star and drive more gas outward. Some elements created or brought up from deeper regions may appear in the atmosphere and eventually become part of the flow of matter entering space. An aging star does not return only unused hydrogen and helium. It also releases carbon, nitrogen, and many other elements that were created or transformed during its lifetime. For low and intermediate mass stars, the final stages of mass loss are an important way of enriching the space between stars. Atoms that once lay deep inside a star can become mixed into the galaxy's clouds of gas, later taking part in the formation of new generations of stars and planets. The Sun and the star that created the Ring Nebula, however, are not massive enough to continue fusing increasingly heavy elements all the way to iron. Nor do they possess cores large enough to collapse into neutron stars and produce the kind of supernova explosion associated with massive stars. Once most of their outer layers have been lost, their evolution follows a path that is less energetic but more prolonged in appearance, an expanding cloud of gas surrounding a hot core, rather than an entire star being torn apart in a single explosion. This distinction is important when speaking about the death of the Sunday. The phrase, dying star, can sometimes bring to mind a violent explosion in which light flares and matter is thrown outward almost instantly. For the Sun, the ending will be more like a slow dismantling. The star will lose material through stellar winds and long episodes of instability until the mass of its outer envelope has been greatly reduced. As more matter escapes, gravity will hold the remaining layers less tightly, allowing the rate of mass loss to increase even further. During some stages, the rate of mass loss becomes enormous compared with the earlier life of the star, producing a dense outflow often called a superwind. Over only a few thousand years, the star may release a significant portion of its remaining envelope. This interval is extremely brief compared with the billions of years spent on the main sequence, yet it supplies much of the material that will later appear in the nebula. Older layers of gas lie farther away, newer ones remain closer to the star, and differences in speed may cause them to collide, compress, or form complicated boundaries. When the gas first leaves the star, it may be too cool and too neutral to glow strongly in visible light. Dust absorbs some of the radiation and remits it at infrared wavelengths, making the system more prominent to telescopes sensitive to that part of the spectrum. Seen only with the eye, the aging star may be partly hidden within the very material it has just released. The familiar planetary nebula has not yet appeared, because the core inside is still not exposed enough to flood the entire cloud with powerful radiation. As the outer envelope thins, what remains of the star begins to contract. Its surface temperature rises, even as its overall size decreases dramatically. The star changes from an enormous object with a relatively cool surface into a much smaller but far hotter core. On the timescale of stellar evolution, this transformation happens quickly. If the core becomes hot before the gas has traveled too far and grown too thin, ultraviolet radiation will ionize the surrounding material and cause the cloud to begin glowing. The timing between these two changes is crucial. If the core evolves too slowly, the gas may disperse before it is illuminated strongly enough, leaving the nebula faint and difficult to detect. If the core heats up while the cloud is still relatively close and dense, a clear planetary nebula can appear. The star's original mass affects this timing, so not every sun-like star leaves behind a brilliant cloud like the famous examples seen in the sky. In the Ring Nebula, the gas remained dense enough to form a prominent structure by the time the central core had become extremely hot. The bright band, the elongated regions of gas, and the faint outer layers may correspond to different episodes of mass loss. Some material was released while the star was still very large and cool, while other parts emerged near the end of the process, when the outflow changed speed and the core began to appear. The object we see today is the result of many layers of time overlapping, not a single shell thrown outward in one isolated event. Astronomers trace this history by measuring the distance of each layer from the central star, its expansion velocity, and its state of ionization. Regions farther away usually left the star earlier, although differences in speed can make the picture more complicated. Chemical composition offers clues about which stellar layers the material came from, while shape reveals the directions in which gas escaped most easily. Each measurement provides only one part of the story, but together they show that the star released its outer layers through a succession of stages. This process also reshapes any surviving planetary system. As the star loses mass, the outer orbits expand, while smaller bodies may be disturbed by the changing gravitational field and by interactions among the planets. Gas and dust move through the entire system, but the outflow remains far too thin to sweep large planets outward, the way wind on Earth moves lightweight objects. The main long-term effect comes from the fact that the system's central star has lost a significant portion of its mass, leaving its gravitational architecture permanently altered. After the final episodes of mass loss, the star's former shape has almost disappeared. What was once its atmosphere has expanded into a region many times larger than the space occupied by the inner planets. At the center, only the hot contracting core remains, preparing to become a white dwarf. The surrounding gas has not vanished, but the star no longer holds it as it once did. Each year, the shell moves farther away, its density falls, and its boundaries gradually blend into the interstellar environment. At this point, an ordinary star has nearly completed the journey toward becoming the scene now observed in the constellation Lyra. The material needed to form the ring has already been released. The large-scale structure has begun to take shape, and the hot core is emerging from behind the dust and gas. The cloud does not yet produce its own brilliant glow. It is waiting for the radiation from the center to become powerful enough to transform the star's former atmosphere into a nebula visible from thousands of light years away. For a brief interval between two stages, the remaining star may sit within a vast cloud of gas without yet creating anything resembling the Ring Nebula. Its outer layers have already left their former positions, and dust and gas continue spreading into space. But most of the material is still too cool and too neutral to glow strongly at wavelengths visible to the human eye. Seen only in ordinary light, the system might appear as an aging star, shrouded in a faint veil of dust, rather than a clearly defined ring of gas against the sky. The transformation begins at the center. After losing nearly all of its outer envelope, the stellar core is no longer hidden beneath the enormous atmosphere that once made the star a red giant. It contracts rapidly, its radius shrinking as its surface temperature rises to an extreme level. The core's total light output may not increase in the same way, but its energy gradually shifts toward shorter wavelengths. A growing portion emerges as ultraviolet radiation, invisible to the human eye yet powerful enough to affect the atoms in the surrounding cloud. The gas released by the star consists mainly of hydrogen and helium, with smaller amounts of oxygen, nitrogen, carbon, and many other elements. Under ordinary conditions, each hydrogen atom contains a single proton in its nucleus, with one electron bound to it. When an ultraviolet photon carrying enough energy strikes the atom, it can remove that electron. The atom then becomes an ion, while the freed electron moves through the surrounding gas. This process is known as ionization. The entire cloud does not change all at once. The strongest radiation first affects the region closest to the stellar core, where high-energy photons remain abundant. As the temperature of the central star continues to rise, the ionized region expands outward. The boundary between the strongly affected gas and the material that remains relatively neutral moves through the shell, creating several zones with different physical states. Regions near the core may contain ions that require very high energies to form, while farther out lie layers where the gas is ionized to a lesser degree. The removal of electrons from atoms is not, by itself, the complete source of the nebula's light. In the thin gas, free electrons can encounter ions and recombine with them. An electron does not necessarily return immediately to the lowest possible energy state, but often passes through several intermediate levels. Each time it drops to a lower level, it releases a photon at a specific wavelength. Countless events like these occur throughout the cloud, converting invisible ultraviolet energy from the stellar core into light that telescopes can detect. Hydrogen produces some of the nebula's most prominent emission lines. One lies in the red part of the spectrum and is often used to trace ionized gas in nebulae. Oxygen also contributes strongly, especially in forms that have lost several electrons. Some oxygen lines fall within the green and blue regions of the spectrum, helping create the familiar colors seen in astronomical images. Nitrogen is often more prominent in the outer regions or in areas with lower levels of ionization. When the data is combined into a color image, the distribution of different elements and ionization states appears as layers resembling colored bands arranged around the core. These colors are not simply paint applied to the cloud. Each glowing region reflects the physical conditions present there, even though the image may be processed to make different wavelengths easier for the human eye to distinguish. Areas close to the radiation source generally receive higher energy photons. Farther from the center, some of those photons have already been absorbed, so the state of ionization changes. Temperature, density, and chemical composition together determine which emission lines will be strongest at each location. In this way, an image of a nebula can become a map of energy. Regions of different colors are not only visually beautiful, they also record how radiation from the core travels through the material. Astronomers compare the strength of many spectral lines to estimate electron temperature, gas density, and the degree of ionization. The data reveals which areas are most strongly affected by the central star, which have cooled, and where molecules or dust have remained protected from complete destruction. Some of the nebula's emission lines once puzzled the first astronomers to study its spectrum. They did not match the known signatures of elements observed in laboratories at the time. For a while, scientists even considered the possibility that a new element might exist within nebulae. Physicists later realized that many of these lines came from transitions that rarely occur in the dense environments found on Earth, but can take place in the extraordinarily thin gas of space. In a laboratory or a planetary atmosphere, an atom in an excited state will often collide with another particle before it has time to release certain kinds of photons. Its energy is then transferred through the collision rather than emitted as light. Inside a nebula, particles are separated by far greater distances, allowing an atom to remain in an unusual state for longer before finally releasing a photon. The lines once described as forbidden do not violate the laws of nature. They are simply very rare under the conditions of matter familiar on Earth. The gas in the Ring Nebula is so thin that a small volume by everyday standards may contain far fewer particles than the air inside a room. Yet the shell extends across an immense distance. When a telescope looks through a great depth of the cloud, the light from countless atoms adds together, becoming strong enough to form a clearly visible glowing band. The density at any one point is low, but the enormous scale of the structure makes up for that emptiness. This also explains why the cloud does not shine like a flame. Fire on Earth is a chemical reaction in a relatively dense environment, where fuel combines with an oxidizing substance and releases heat. The nebula is not burning in that way. Its light appears because atoms absorb energy from ultraviolet radiation, become ionized or excited, and then release photons as they return to lower energy states. The energy source is the hot stellar core. The gas merely transforms and remits part of that energy. Nor does the nebula simply reflect light in the way the moon reflects sunlight. In a reflection nebula, dust grains scatter light from a nearby star without necessarily changing the atomic structure of the gas to the same degree. Here, much of the characteristic light is produced within the cloud itself through atomic processes. The photons that eventually reach Earth carry wavelengths associated with hydrogen, oxygen, and other elements rather than simply reproducing the light emitted by the core. A very small core can illuminate a region of gas thousands of times larger than itself because its radiation spreads in every direction. Yet this ability to light the cloud does not last forever. The nebula continues to expand, causing its density to fall. At the same time, the stellar core approaches the white dwarf stage and gradually cools. There is only a relatively brief period when the core is hot enough to ionize the gas, while the shell remains close enough and dense enough to glow clearly. This is the window during which a planetary nebula becomes a prominent object. If the gas has traveled too far before the core grows hot, the glow will be weaker and the structure more difficult to observe. If the central star evolves quickly enough, ultraviolet radiation appears while the cloud is still relatively dense, producing a brighter nebula. The relationship between the rate at which the core contracts and heats up and the rate at which the gas expands makes the star's original mass an important factor. Two stars that appeared similar during their stable lives may still leave behind very different nebulae. In the case of the Ring Nebula, the timing allowed the gas to become clearly illuminated. The central star is now extremely hot, although it appears fairly faint in visible light because of its small size. Its ultraviolet radiation keeps much of the cloud ionized. The main band stands out where the material is denser, and our line of sight passes through more gas, while thinner regions or areas in different ionization states create fainter structures. The darkness near the center is not a sign that radiation cannot pass through it. On the contrary, the inner region is strongly affected by the hot core, but its low density means that less total light may accumulate along our line of sight than through the thick outer band. Some high-energy ions appear near the center, while denser material is concentrated within the torus-like structure that creates the familiar outline. The final image is shaped by density, temperature, composition, and geometric depth all at once, not simply by distance from the star. The outermost layers may not yet be fully ionized. Where ultraviolet radiation has weakened, molecular hydrogen, dust, and carbon-bearing compounds may still survive. The boundary between the ionized region and the molecular gas is not perfectly sharp. It is a transitional zone where the chemistry changes according to the amount of energy received. These partly shielded regions become especially important in infrared observations because they contain structures that visible light does not fully reveal. The central source of light also influences the shape of the nebula over time. As the gas is heated and ionized, its pressure rises, causing the material to continue expanding and interact with outflows released earlier. A fast wind from the hot core can catch up with the slower, denser wind produced during the previous giant star phase. The collision between these two flows compresses the gas into brighter layers, creating boundaries, delicate filaments, and regions of higher density. The prominent ring is not simply the star's former atmosphere standing motionless beneath the light of the core. It is a dynamic environment shaped by radiation, flowing gas, and expansion. Some regions appear bright because they contain more material, while others stand out because their state of ionization produces strong emission at the wavelength being observed. The boundaries continue to shift as the cloud grows larger, and the stellar core changes in temperature and brightness. These motions unfold far too slowly for the human eye to notice during a single night at the telescope. Over many years, however, precise measurements can reveal the expansion. By combining the velocity of the gas with its observed size, astronomers estimate that the nebula is still relatively young by astronomical standards and has existed in this form for only a few thousand years. The exact figure depends on which part of the structure is measured and which model of motion is used, but the entire glowing phase remains extremely brief compared with the billions of years during which the star lived in a stable state. The light now reaching Earth is evidence of a rare transitional moment. The gas no longer belongs to the star, yet it has not fully dissolved into the interstellar environment. The core can no longer continue its life as an ordinary star, but it still retains enough heat to illuminate the surrounding material. Two components that once formed a single stellar body have now moved far apart, yet they remain connected through radiation. When the sun reaches a similar stage, the basic mechanism will be the same. Its outer layers must be released, the core must heat up quickly enough, and the cloud must retain a suitable density to absorb energy and glow. We cannot yet know how closely the sun's nebula will resemble the object in Lyra in shape, brightness, or duration. What can be predicted with greater confidence is that, if it becomes clearly visible, its light will also come from atoms that once belonged to the sun itself, awakened by ultraviolet radiation from the remaining core. Through this mechanism, the lost atmosphere does not immediately disappear into darkness. For a brief interval in cosmic time, it becomes the most visible part of the former star, expanding into layers of color around a tiny core nearly overwhelmed by the glow it creates within the cloud. The ring in the sky is neither burning on its own nor merely reflecting a source of light at its center. It is stellar material responding to energy from the remaining core, atom by atom, across an immense region of space. From a distance, the band of gas may appear smooth and continuous. Deeper observations reveal that it is divided into countless filaments, knots, and clumps of varying density. Some regions are thick enough to shield molecular gas from intense radiation, leaving dark patches and elongated tails extending outward. When Webb observes the ring in infrared light, the seemingly smooth structure separates into tens of thousands of smaller regions, each preserving its own part of the interaction between the hot core and the star's former atmosphere. Text. From Earth's distance, the glowing band around the central star appears soft and almost continuous, as though the entire layer of gas had been spread evenly into one broad ribbon. Only when a telescope reaches sufficiently high resolution does that smoothness begin to dissolve. Fine filaments appear first, followed by small dark regions between the brighter areas, until the entire ring gradually reveals itself as a collection of countless individual structures. Webb has shown that the nebula contains roughly 20,000 dense clumps of gas, most of them rich in molecular hydrogen, crowded within and around the main ring. That number changes the way we see the cloud. This is not a uniform shell expanding outward, but an uneven environment at every scale. Some thin regions allow radiation to pass through relatively easily, while nearby knots of gas are dense enough to preserve molecules and dust. Each knot occupies only a tiny fraction of the nebula as a whole, but when tens of thousands of them are gathered within the same region, they create a complicated boundary that infrared images can separate far more clearly than before. The word dense must be understood here by the standards of a nebula, not by everyday experience. Even the most prominent clumps are far thinner than the air around us. If a small volume of that material were brought into a room, it would still seem almost like a vacuum. What makes these regions distinct is that their density is significantly greater than that of the neighboring gas, and that relative difference is enough to alter their temperature, chemistry, and ability to resist radiation from the stellar core. Some estimates suggest that each clump may contain an amount of material comparable to the mass of Earth. That comparison may make them sound like small planets, but the two kinds of objects are entirely different. This mass is not compressed into a rocky sphere only a few thousand kilometers across. It is dispersed through an immense region of gas, with no surface, no independent rotation like a world, and no self-gravity strong enough to hold it in a rounded celestial body. What is remarkable is the large amount of matter distributed with extreme thinness, not the presence of thousands of hidden planets within the ring. Molecular hydrogen consists of two hydrogen atoms bound together. It is a familiar form of hydrogen in cold, relatively well-shielded regions of gas, but it cannot easily survive prolonged exposure to intense ultraviolet radiation from an extremely hot stellar core. High-energy photons can break the bond between the two atoms and then continue ionizing the remaining gas. Webb's detection of many regions rich in molecular hydrogen shows that places still exist within the glowing band where the material is dense enough to escape the strongest effects of the central radiation. Each clump acts almost like a small shelter in space. The side facing the core receives stronger radiation and is gradually heated and eroded. The region behind it is better protected, allowing molecules and dust to survive under gentler conditions. Extending away from the star, many of these structures form tails or elongated streaks because the shadowed region behind them remains in a different state from the surrounding environment. When thousands of these shadows point outward, the nebula's ring develops features resembling spokes or fine rays radiating from the center. These rays are not streams of matter being fired outward by the core like beams from a lamp. They result from the difference between regions exposed directly to radiation and those lying in the shadows of dense gas clumps. In protected areas, molecules may form or survive longer, while exposed material becomes ionized and glows in a different way. A feature that appears to show powerful motion in an image may sometimes be produced by light and chemistry, rather than by a distinct stream of gas rushing outward. Hubble had already recorded unusual dark knots along the inner edge of the ring, along with elongated spoke-like structures. Webb's greater infrared sensitivity and resolution have made the relationship between them much clearer. Areas that once appeared only as small dark patches are now recognized as structured regions of molecular gas, while the trails behind them reveal how radiation from the core passes through such an uneven environment. The near-infrared camera is particularly well suited to separating the small details within the main ring. At these wavelengths, certain emissions from molecular hydrogen and related material become easier to detect, while dust and gas do not obscure the view in quite the same way they do in visible light. The result is not merely a sharper version of an older photograph. The structure breaks apart into countless fine filaments and alternating bright and dark regions, making the ring look more like an environment being slowly eroded than a stable layer of gas. Inside the thick ring lies a region of much hotter gas. There, radiation from the core arrives more directly, molecules struggle to survive, and atoms are often found in higher states of ionization. The contrast between the extremely hot inner gas and the molecular hydrogen-rich knots in the ring creates a clear chemical boundary. Even within the same nebula, two nearby regions may contain matter in entirely different states simply because their density, degree of shielding, and distance from the radiation source are not the same. That boundary is not a perfect circle. The side of each clump facing the core is eroded at its own rate, depending on the clump's size, density, and location. A small knot may lose its outer layers more quickly, while a larger one can preserve its molecular center for longer. Gaps between them allow radiation to penetrate deeper into the ring. Instead of a smooth ionization front, moving evenly around the nebula, light passes through a landscape of gas filled with openings, protrusions, and sheltered regions. There is still no single explanation for how these clumps form that applies to every planetary nebula. One possibility is that they began as small variations in density already present in the outflow, while the star was still losing its outer layers. When the slow stellar wind was overtaken by a faster wind from the hot core, the gas became compressed, allowing slightly denser regions to develop into distinct knots. Instabilities at the boundaries between layers moving at different speeds, temperatures, or densities may also have broken the shell into smaller structures. Another explanation suggests that some of the fragmentation appeared as ionizing radiation swept through the cloud. Denser regions resisted erosion for longer, while thinner areas lost material more quickly. Differences that were initially small gradually became more pronounced, leaving compact knots surrounded by ionized gas. Both the motion of the outflows and the effects of radiation may have contributed. A single process does not necessarily have to account for all 20,000 structures. Their enormous number shows that the final loss of gas did not occur across a perfectly even surface. The atmosphere of the aging star had already been disturbed by vast convection cells, pulsations, and repeated stellar winds of varying strength. These asymmetries may have been carried outward before the nebula began to glow. Once the hot core was exposed, its radiation continued carving the material, turning small differences into an increasingly visible network of filaments and knots. The dense clumps do not survive forever. The side facing the star is heated, and material from the outer layers escapes into the surrounding ionized environment. This process is often described as photoevaporation, although it is not like a drop of water turning into vapor in a kitchen. Energy from the core heats the gas, raises its pressure, and drives material away from the surface of the knot. Over time, the structure grows smaller, its tail changes, and gas that was once protected begins to emerge. The rate of erosion depends on the intensity of the radiation and the size and density of each knot. Some may survive through most of the nebula's luminous lifetime, while smaller structures are destroyed sooner. The stellar core does not maintain the same level of radiation forever. As it moves deeper into the white dwarf stage and gradually cools, its ionizing output declines, but by then the cloud has also expanded and become thinner. The gas knots take part in a slow race between erosion, expansion, and the fading of the central energy source. Within the main shell, a thin band of emission has also been detected from carbon-bearing molecules, known as polycyclic aromatic hydrocarbons, usually abbreviated as PAHs. The long name may make them sound unfamiliar, but they are essentially carbon-based molecules built from several linked rings. They are common in many regions of space, especially where dust and radiation are present in conditions that allow them to emit infrared light. The presence of a PAH band within the ring is notable because the nebula's chemical environment is not necessarily one in which these molecules would always be expected to form easily. The original star and the material it expelled had their own chemical composition, while intense radiation can destroy complex molecules. Regions shielded by dense gas knots may provide more favorable conditions for carbon chemistry to continue, or allow the molecules to survive long enough for Webb to detect them. These observations show that even during the final stage of a star's life, the surrounding cloud is not merely a collection of isolated atoms. It also contains an evolving network of chemistry. The word organic should not be understood as evidence of life when used to describe carbon-based molecules. In astrochemistry, compounds such as PAHs can form through processes entirely unrelated to biology. They are important because they show that carbon can assemble into complex structures within gas and dust in space, while also helping researchers trace regions of material exposed to moderate levels of radiation. They reveal chemical conditions, not living organisms within the nebula. On the largest scale, the ring continues to expand like a shell around the stellar core. On smaller scales, each gas clump has an illuminated face, a shadowed region, an outer layer being eroded, and a protected molecular interior. 20,000 such structures turn the nebula into a system of countless local environments, where the same radiation produces different results depending on how much material lies in its path. The beauty of the entire glowing band is built from these tiny irregularities. This fragmentation also affects how astronomers estimate the nebula's mass and reconstruct its history of mass loss. If the cloud is treated as a smooth shell, some of the material concentrated within dense knots may be misjudged. Cold molecular gas does not glow strongly in the familiar optical emission lines, making observations across multiple wavelengths essential. Infrared data helps recover material that was once hidden from measurements based mainly on ionized gas, bringing our picture of the star's former atmosphere closer to completion. Each knot also preserves a small fragment of the transition between the red giant stage and the planetary nebula phase. The clumps may contain material released at slightly different times, compressed to different degrees, and then exposed to radiation for different lengths of time. No individual knot can be read as a complete page of the calendar, but their overall distribution shows that the outflow was once uneven and that the shell was later shaped by radiation and stellar winds. A similar future may await the Sun's outer layers, although we cannot know whether its nebula will contain the same number of knots or develop an identical structure. The way these instabilities grow depends on the mass of the core, the speed of the winds, the chemical composition, the star's rotation, and the possible presence of a companion object. The Sun will follow the same broad path, losing its outer layers, exposing a hot core, and illuminating the surrounding gas. The small-scale details within that shell remain the most difficult part to predict. Webb did not transform the ring into an entirely new object. It revealed what had always existed within the faint glow. The seemingly continuous band of gas separated into thousands of molecular knots, outward-pointing shadows, and a narrow line of carbon emission within the shell. What once appeared calm is undergoing constant erosion, while the darker regions are not places devoid of information, but often areas where denser material is shielding what lies behind them. Beyond the main ring, the brightness falls rapidly and the structures become more difficult to see. Yet the gas does not end at the prominent boundary visible in images. Mid-infrared observations reveal a faint molecular halo extending farther outward, where broad arcs appear at nearly regular intervals. The small gas clumps preserve the story of fragmentation within the ring, while the more distant arcs may record a longer rhythm in the loss of the star's atmosphere, a rhythm that may not have been created by the central star alone. Beyond the prominent glowing ring, where the colors in familiar images begin to fade into the background of space, the cloud of gas continues to extend outward. This region is far dimmer than the main structure, and in earlier observations, many of its details nearly blended into the faint halo surrounding the nebula. When Webb's mid-infrared instrument examined this area, the outer edge no longer appeared as a uniform mist. Within the halo of molecular gas lies a series of broad curves arranged in nearly concentric patterns around the star that created them. There are about 10 such arcs just beyond the edge of the main ring. They do not shine as a set of complete circles, nor do they have sharp boundaries like lines drawn with a compass. Some sections are easier to see than others because gas density, viewing angle, and the sensitivity of the instrument all affect their appearance. Even though they do not form perfect circles, the relatively regular spacing between the arcs makes them difficult to dismiss as random ripples in the cloud. That regularity carries the story back to the time when the star was still losing its atmosphere. If one layer of gas was released and allowed to expand for a period of time, followed later by another layer, the two would eventually lie at different radii. Their separation, combined with the expansion velocity, can reveal the time between episodes of mass loss. From the curves recorded by Webb, researchers estimate that a new feature may have formed roughly once every 280 years. 280 years is a long interval in human history, but extremely brief within the billion-year lifetime of a star. It is also too long to be directly linked to the pulsations lasting months or years that are common in many aging giant stars. Thermal pulses deep inside the star occur on a different rhythm, usually separated by much longer intervals. No single known process within a star of this kind naturally produces such a regular pattern on precisely this timescale. When no suitable clock can be found within the star itself, attention shifts to the environment around it. A companion object moving in a wide orbit could return to a similar position every few centuries, repeatedly disturbing the gas flowing away from the primary star. The companion would not need to shine brightly or have a mass close to that of the dying star. The gravity of a smaller star, moving regularly through the expanding material, could be enough to imprint a rhythm into the gas. The current hypothesis places the possible companion at a distance comparable to the scale between Earth and Pluto. This would be a wide orbit compared with the distances between the Sun and the rocky planets, yet still close enough for the two stars to remain part of the same gravitational system. At such a distance, one orbit could take hundreds of years, matching the rhythm inferred from the arcs. As the primary star lost gas, its companion would move through the outflow, altering the density and direction of the material around it. This influence would not resemble a solid object physically carving lines into the gas. Gravity acts from a distance, gently drawing material toward the companion and concentrating part of the flow along its orbit. As both stars continued to move, the denser region of gas would shift as well. Over many revolutions, the outflow could be organized into a broad spiral around the system's shared center. A three-dimensional spiral, when viewed from a suitable angle, does not necessarily resemble the familiar shape of a spiral. Different sections may overlap in the flat plane of an image, creating the appearance of several concentric arcs. This interpretation explains why the curves are spaced relatively evenly, without requiring the primary star to eject complete shells at regular intervals. Instead, the gas may have been released fairly continuously, while the orbital motion of the companion produced periodic changes in density. Similar structures have been observed around other aging stars that are losing mass. When a stellar wind expands while its source moves together with a companion, the material can form enormous spirals, somewhat like the trace of a slowly rotating sprinkler. The spacing between the spiral arms depends on the speed of the wind and the orbital period. Astronomers can use this geometry to infer the presence of an object that is difficult to observe directly. In the case of the ring in Lyra, the arcs are not enough to determine every property of the possible companion. They do not yet reveal its exact mass, stellar type, or orbit with certainty. The interpretation also depends on the estimated expansion velocity and on the assumption that the arcs truly belong to the same repeating structure. What is most notable is the agreement between the 280-year rhythm and a wide orbit, not the direct appearance of a second star in the image. Finding such an object directly is not simple. The central star remains extremely hot. The surrounding gas produces a complex field of light, and bright points along the same line of sight may belong to unrelated stars in the foreground or background. A low-mass companion could also be far fainter, especially if it lies close to the central source in the image. In astronomy, some objects are first recognized not through their own light, but through the order they leave behind in the environment around them. Text. The arcs act like gravitational traces. No one can see gravity itself, but matter responds to it. A distant planet may be detected through the wobble of its star, a black hole may reveal itself through the motion of surrounding gas, and a faint companion star may be inferred from the way a stellar wind has been arranged. In each case, the object does not need to appear as a clearly visible point of light. Its long-term influence is enough to create a measurable pattern. The possible presence of a companion star also helps explain a broader question about planetary nebulae. An isolated star is basically spherical because gravity pulls matter toward its center from every direction. If it loses gas relatively evenly, the shell it creates should also tend toward a nearly spherical shape. Yet many observed nebulae have thick rings, symmetrical twin lobes, narrow jets, spiral structures, or layers of gas displaced from the center. This diversity suggests that their shapes are often influenced by more than the simple expansion of an isolated star. A companion star can affect the system to different degrees. If it is very close, it may enter the outer atmosphere when the primary star swells into a giant, producing a period of intense interaction and causing the entire system to lose material more rapidly. At greater distances, it does not become immersed in the atmosphere, but its gravity can still reshape the wind, creating regions of higher and lower density that repeat along the orbit. The case proposed here would involve a gentler and more prolonged influence, strong enough to leave behind the arcs without necessarily dividing the entire structure into two large lobes. This also connects two very different scales of structure revealed by Webb. Within the main ring, tens of thousands of gas clumps reflect fragmentation, shielding, and erosion on small scales. Farther out, the broad arcs preserve a rhythm lasting centuries. One group of features tells the story of radiation acting on the material after the hot core was exposed. The other may have originated while the star was still releasing its atmosphere and moving together with a companion. The outer layers of gas left the star before the material in the bright main ring. They continued expanding, cooling, and becoming thinner, so their emission stands out more clearly in the mid-infrared than in visible light. Miri's ability to detect cool, faint material brought these curves into sharper view. A telescope observing the same object at a different range of wavelengths might capture the main ring beautifully while missing the earlier history preserved beyond its brightest boundary. The edge of the nebula is therefore no longer where the story ends. It becomes a region containing older memories of the mass loss process. Each more distant arc has had additional time to travel away from the center. If the orbital interpretation is correct, the series of curves preserves several revolutions of the two stars during the period when the outer atmosphere was being released into space. The gas accidentally recorded part of the system's motion, much like a succession of ripples, preserving the rhythm of the source that created them. As compelling as it may be, the companion star hypothesis must remain in its proper place. The relatively even spacing between the arcs is observational data. The period of about 280 years is inferred from their structure and expansion velocity. A low-mass object in a wide orbit is a plausible explanation for that rhythm. These three layers of information do not carry the same level of certainty, and presenting them as a single confirmed conclusion would remove an important part of how science works. Future observations may search for a slight motion of the central star, the faint light of a companion, or spectral signs consistent with a binary system. Models must also reproduce not only the spacing of the arcs, but the shape of the main ring, the extended gas, and the large-scale distribution of matter. A hypothesis becomes stronger when it explains several features at once, rather than matching only one isolated detail. If the companion is eventually confirmed, the ring will no longer be understood solely as the product of a dying star. It will be the result of two objects orbiting one another, with one star supplying most of the gas while the other quietly shaped the way that gas spread outward. The famous image of a solitary core within the cloud would then show only the most visible part of the system. Its true history would have been written by more than one member. This possibility places a clear limit on comparisons with the future of the Sunday. There is currently no evidence that the Sun has a companion star in a similarly wide orbit. If the structure of the Ring Nebula was significantly influenced by a second object, the Sun would not necessarily produce the same arcs, the same thick band, or the same appearance as it loses its outer layers. Two stars may pass through similar physical stages, yet leave behind very different images because the environments around them are not the same. That difference does not make the nebula any less useful as a window into the future. It makes the comparison more precise. The nebula shows that a star belonging to a group similar to the Sun can lose its atmosphere, illuminate the released gas, and leave behind a hot core. The outer curves remind us that the final shape also depends on rotation, magnetic fields, the rhythm of mass loss, and other objects sharing the system. Across the scale of the entire image, the possible companion is almost absent. There is no prominent point of light beside the core, announcing its role. Instead, there are about 10 faint arcs, each lying farther out than the one before it, together preserving a rhythm that the primary star would struggle to create alone. This is one of the ways the universe leaves behind information. An object may disappear from view while its influence remains preserved in the motion of matter. The arcs carry the story beyond the brightest boundary of the ring and then lead it back toward the center. Beneath all the layers of gas, molecular structures, and gravitational traces, the remnant of the original star is extremely small compared with the cloud around it. It has lost nearly all of its atmosphere and no longer produces energy as the Sun does today, yet it remains hot enough to sustain the glow of the entire nebula. As the arcs continue drifting outward, the central core is entering a much longer-lasting state. Its size will shrink to roughly that of a planet, while the matter compressed into such a small volume will reach densities far beyond those of any rocky world. This tiny remnant will outlast the ring, the arcs, and the brilliant phase we are observing now. Long after the former atmosphere has dispersed into the galaxy, it will remain as the final remnant of the star that once shone at the center of its system. Text: amid the vast layers of gas in the Ring Nebula, the central star appears as such a tiny point of light that it is easy to overlook. Most attention is naturally drawn toward the colorful band of gas, the dense molecular knots, and the faint arcs along the outer edge. Yet all of that light still depends on a single object at the center, the core left behind after the star lost nearly all of its atmosphere. The ring may be the most striking part of the image, but the core is what will endure for far longer. When the outer layers of a star like the Sun are released, the remnant does not continue contracting without limit. Before this point, the core has passed through stages of hydrogen and then helium fusion, producing material composed mainly of carbon and oxygen. The star is not massive enough to raise its central temperature to the level required for carbon to continue fusing steadily into heavier elements. The nuclear energy source that kept the star shining through most of its life gradually comes to an end, leaving behind a hot, dense core with no suitable fuel for another cycle of fusion. This object is on its way to becoming a white dwarf. The name may suggest a star that is simply smaller and weaker than the Sun, but the difference is far more profound. A white dwarf is not a miniature version of an ordinary active star. It is an exposed stellar core, with most of its remaining matter compressed into a sphere roughly the size of Earth. Within a volume no larger than a rocky planet, it may contain a substantial fraction of the Sun's mass. This concentration produces densities that are difficult to compare with familiar matter. A piece of white dwarf material about the size of a sugar cube could weigh several tons under Earth conditions. Atoms no longer maintain the wide separations found in ordinary material. Immense pressure forces electrons into such confined conditions that the rules of quantum mechanics begin to determine the structure of the entire star. For most of the Sun's life, the pressure-resisting gravity comes from hot gas and the energy generated by fusion. Once that energy source disappears, ordinary matter can no longer maintain its former state. The core contracts until the electrons are forced extremely close together. According to the Pauli exclusion principle, no two electrons can occupy exactly the same quantum state. As space becomes increasingly crowded, the electrons are forced to fill higher energy states, producing a form of pressure that does not depend directly on temperature. This is known as electron degeneracy pressure. It prevents the core from collapsing any farther under gravity, even though nuclear reactions no longer provide energy as they once did. In an ordinary star, balance is maintained by heat and gas pressure. In a white dwarf, the structure is supported by the quantum behavior of electrons. A phenomenon operating on the scale of tiny particles becomes the foundation holding up an object with nearly the mass of a star. This does not mean that a white dwarf is completely cold or dark. When it first emerges from the surrounding gas, it is extraordinarily hot. The core that once lay deep inside the star is now exposed directly to space, still carrying heat accumulated during earlier stages of evolution. Its surface may be many times hotter than the present surface of the Sun, producing large amounts of ultraviolet radiation and ionizing the gas around it. The glow of the nebula during this stage is evidence that the core still retains an extremely high temperature. A high temperature does not mean that it continues producing significant energy through fusion. A white dwarf shines mainly because it is releasing stored heat. It is like an object that has been removed from a furnace but remains hot, except that its heat and density are far beyond those of any ordinary object. No stable nuclear reactor continues to feed its light from within. The core is simply radiating its remaining thermal energy slowly into space. The cooling process takes an immense amount of time. At first, the white dwarf is hot and relatively bright, but its heat gradually declines. No new fuel is supplied, and there is no vast outer envelope left to sustain another cycle of stellar evolution. Over billions of years, its light weakens, its color changes, and the object becomes increasingly difficult to detect. The universe is not yet old enough for any white dwarf to have cooled completely into the theoretically dark state predicted for its distant future. That final state is commonly called a black dwarf. No such object has ever been observed because the time required for a white dwarf to cool until it emits almost no light is far longer than the present age of the universe. The name describes an extremely distant theoretical future, not a population of stars already discovered by telescopes. Every white dwarf that exists today still retains some heat from its earlier history. The core of the Ring Nebula is at a much earlier stage. It remains hot enough to keep the surrounding gas ionized. As its ultraviolet radiation weakens, atoms in the nebula will begin recombining more quickly than they are ionized. The emission glow will gradually fade, not because the gas immediately disappears, but because the energy source making it shine is no longer as powerful. At the same time, the cloud will continue expanding, reducing its density and making it progressively less capable of producing a clearly visible glow. The brilliant ring and the stellar core are following two very different timescales. The nebula remains prominent for only a few tens of thousands of years, an extremely brief interval compared with the star's billion-year lifetime. The white dwarf may continue to exist far longer than almost every other structure around it. The band of gas will gradually merge into the interstellar medium, while the core continues orbiting through the Milky Way as a tiny point of light, carrying the final material that once belonged to the original star. The white dwarf's small size also affects its appearance. An object with an extremely hot surface, but a very small emitting area, may be less prominent than a cooler star with a much larger surface. This is why the central core is easily overwhelmed by the nebula in photographs. It supplies the ultraviolet photons that make the entire cloud glow, yet occupies only a tiny point within a structure vastly larger than itself. Mass determines whether electron degeneracy pressure is strong enough to support the core. If a white dwarf becomes too massive, gravity can overcome that resistance. The theoretical limit is about 1.4 times the mass of the Sun and is known as the Chandrasekhar limit. The core left behind by an isolated Sun-like star remains well below that threshold, allowing it to stay stable over extremely long periods instead of collapsing further into a neutron star. In a close binary system, the story can become more complicated. A white dwarf may sometimes draw material from a companion star, changing its mass and the conditions at its surface. Some systems can produce nova eruptions, while in more exceptional cases, a white dwarf may take part in a Type Ia supernova. These paths are not part of the ordinary isolated evolution expected for the Sun, nor are they needed to explain the central core of the Ring Nebula. They simply show that this small remnant may still have another chapter ahead if its surroundings provide additional material. For the Sun, the future core will most likely be a carbon-oxygen white dwarf with a mass significantly lower than the Sun has today. The rest of the mass will already have been carried into the expanding gas or released into the interstellar medium. The star that once controlled the planet's orbits with its full original mass will retain only its concentrated core, changing the gravitational field of the system according to how much material has been lost. Although it is roughly the size of Earth, a white dwarf is not a planet with a surface upon which anything could stand. Its gravity is vastly stronger than Earth's, its matter exists under extreme conditions, and there is no ordinary layer of soil or rock. If an object moved too close, the difference in gravity between its near and far sides could stretch it, tear it apart, or severely alter its orbit. The surface of a white dwarf is the boundary of a dense body of plasma, not solid ground in the sense associated with rocky planets. A white dwarf's atmosphere is only an extremely thin layer compared with its total mass. Its powerful gravity causes heavier elements to sink rapidly, often leaving hydrogen or helium floating above them. When spectra reveal calcium, magnesium, iron, or other heavy elements in the atmosphere, astronomers have reason to suspect that this material fell in from outside relatively recently. Such evidence has become an important way of studying the debris of former planetary systems. While the nebula still glows, the surrounding gas partly conceals the core's much longer story. Ionized material creates the colors, shapes, and details that attract the eye, while the white dwarf quietly releases heat at the center. Over time, the order of visibility will reverse. The nebula will fade until it is almost impossible to detect, while the core remains a more clearly defined object, even as its own light continues to weaken very slowly. The transformation from a red giant into a planet-sized object shows that most of a star's enormous size never belonged to a solid surface. The star was vast because its hot gaseous layers were held within an extended structure, not because all of its matter had the same high density as the core. When the outer layers drift away, the visible size decreases dramatically, yet a large portion of the mass remains concentrated at the center. What disappears is mainly the immense atmosphere. What remains is the material that once lay deepest within the star. Seen in this way, a white dwarf is not a random fragment left behind after a star's death. It is the core that was built over billions of years. Helium was created from hydrogen, carbon and oxygen were formed during helium fusion, and all of that material was eventually compressed into the final remnant. The history of the star is recorded not only in the gas that escaped, but also in the composition, mass, and temperature of the core left behind. The Ring Nebula allows us to observe two parts of a former star at the same time. The outer region has become a vast, thin cloud. The inner region has contracted into a small, dense object. One is merging into the galaxy, while the other continues to exist as a white dwarf. Layers that once lay beside one another within the same star are now separated by an immense distance, yet the light from the core still connects them within the scene recorded by telescopes. The future sun will undergo the same separation. Atoms from its outer layers will be returned to space, while the carbon-oxygen core remains inside a sphere, roughly the size of Earth. From a star that once contained most of the solar system's mass and supplied nearly all the light received by its planets, it will become a tiny point of light, intensely hot at first, and then slowly cooling across a span of time almost impossible to measure against human history. That core will not mark the complete disappearance of the system. Its gravity will remain, though weakened because the sun will have lost a large portion of its mass. Planets distant enough to survive may continue orbiting the white dwarf along expanded paths. Asteroids, comets, and icy bodies will not all vanish at once. Many will enter a new gravitational arrangement in which the balance among them has changed. As the ring fades, the remaining orbits will become the next part of the story. The central star will no longer resemble the sun, but the surviving worlds will still move around that small core within a system that is darker, wider, and more easily disturbed than before. The future of the white dwarf will not be defined only by how it cools, but also by what continues to exist around it after the former atmosphere has dispersed into space. As the glowing gas surrounding an aging star begins to thin, the most striking scene of its final stages gradually fades away. The nebular ring grows dimmer, the filaments lose their contrast, and the hot core at the center continues contracting into a white dwarf. Yet beyond that cloud, the story of the planetary system is not over. Worlds distant enough to survive the red giant phase continue moving, but they no longer orbit the same star with the same mass or the same gravitational structure as before. For most of the sun's life, the planet's orbits have been held in place by a gravitational field that changes very little. The sun contains most of the mass in the entire system, so the motions of Mercury, Earth, Jupiter, and the more distant bodies are all closely tied to the mass at the center. As the star enters old age and releases a significant portion of its material into space, that gravitational center becomes lighter. The planets are not pushed outward by a wind in the ordinary sense. Their orbits expand because the inward pull holding them around the star has weakened. This motion can be understood by considering a planet traveling along a nearly circular orbit. Its velocity is matched to the gravitational force produced by the star at its present distance. If the central mass decreases slowly, the planet retains most of its existing orbital motion, but the inward pull is no longer as strong as before. The old orbit can no longer remain unchanged, so the planet moves farther away until its motion becomes compatible with the new gravitational field. The mass loss of a sun-like star lasts far longer than the time a planet needs to complete a single orbit. Jupiter takes less than 12 years to travel around the sun, while the star's strongest episodes of mass loss continue for thousands of years. With such a gradual change, the orbit can adjust relatively smoothly instead of being disrupted by a sudden gravitational jolt. Astronomers describe this as a nearly adiabatic response. The system has enough time to adapt continuously as the central mass declines. If the material leaves the star fairly evenly in every direction, the shape of a planet's orbit may not change dramatically. even as the orbit itself grows larger. Its average distance from the future white dwarf may become significantly greater than it is today. The amount of expansion depends on how much mass the Sun loses before becoming a white dwarf. If the star ultimately retains only a little more than half of its original mass, the orbits of the surviving planets will widen by a corresponding amount. Jupiter, Saturn, Uranus, and Neptune will probably survive the red giant phase, although their futures cannot be considered entirely separate from the system's broader changes. Their great distances protect them from being directly engulfed by the Sun's outer layers, but the architecture of the system will have been altered. Jupiter may move into an orbit far wider than the one it follows today, while Saturn and the two ice giants shift outward in a similar way. A system once illuminated by a relatively large yellow star will become one in which these planets orbit a point of light smaller than Earth and steadily fading with time. The expansion of every orbit does not mean the system will simply become an enlarged copy of its former arrangement. The planets will continue exerting gravitational forces on one another, and their actual paths are not perfect circles. As distances change, orbital periods change as well, shifting the gravitational resonances that have existed throughout the system for billions of years. A relationship that once helped stabilize two bodies may weaken, while a new resonance gradually appears elsewhere. Orbital resonance occurs when the periods of two objects form a simple ratio, causing the small gravitational pulls between them to repeat in an organized rhythm. Under the right conditions, this pattern can help stabilize an orbit. Elsewhere, it can accumulate small disturbances and make the orbit increasingly eccentric. The present solar system contains many such regions, especially within the asteroid belt and among objects beyond Neptune. As the central mass decreases, this map of resonances will no longer remain the same. The giant planets may continue along stable orbits for a very long time, but the countless smaller bodies around them will be far more sensitive to this rearrangement. An asteroid is too small to influence a planet significantly, while even a slight change in the pull from Jupiter or Saturn can send it onto a new path. Some objects may be driven farther outward, others may enter the inner regions of the system, and some could pass close to the white dwarf after millions or billions of years. The asteroid belt between Mars and Jupiter offers a clear example. By the time the white dwarf stage begins, many of its members may already have disappeared or shifted into different orbits. Those that remain will have to adjust to a lighter sun and to the new positions of the giant planets. As resonances move through the belt, orbits that were once stable may become chaotic, sending streams of rocky bodies into regions where they rarely traveled before. The moons of the giant planets will continue to be held mainly by the gravity of their parent worlds, but the region in which each planet can retain satellites securely will change as its orbit around the white dwarf expands. Most of the larger moons may remain bound to Jupiter, Saturn, Uranus, or Neptune because they lie deep within the planet's gravitational fields. Smaller satellites on more distant orbits, along with temporarily captured objects, will be more vulnerable to disturbance or escape. During the Sun's period of mass loss, the planets will also move through the expanding flow of material. The gas will be far too thin to create strong drag on large worlds at great distances, although dust, gas, and radiation may affect smaller bodies more noticeably. Even so, the decisive influence on the system's long-term structure will be the change in the central mass and the gravitational disturbances that follow, rather than the direct pressure of the stellar wind. Far beyond Neptune, the Kuiper belt contains many icy bodies with a wide range of orbits. Some are held in resonance with Neptune, while others travel along inclined or elongated paths. As Neptune moves outward in response to the Sun's mass loss, its relationship with these objects will change as well. Some may remain trapped in resonance, others may leave their former configurations, and bodies already near the edge of stability could be pushed onto very different orbits. Pluto and many of the larger bodies in this region may survive as dark, icy worlds orbiting the white dwarf, even though their surfaces will have passed through a period of warming while the Sun was still a red giant. After the outer layers drift away, and the sun's brightness falls sharply, temperatures in the distant system will decline again. Temporary atmospheres, formed during the warmer era, may freeze back onto the surface or escape into space, leaving behind landscapes reshaped by a cycle that no object in the present solar system has ever experienced. Farther out lies the Oort cloud, a hypothetical population of countless icy bodies near the outer edge of the sun's gravitational influence. These objects are already only weakly bound to the system. When the sun loses nearly half of its mass, its ability to retain the most distant members will decline. Tidal forces from the Milky Way, together with passing stars, may remove a significant portion of them and turn them into objects drifting freely through interstellar space. Some comets will not leave the system immediately, but will instead be sent onto elongated orbits leading toward the inner regions. This disturbance may continue long after the planetary nebula has disappeared. The white dwarf at the center may appear quiet, while the outer system continues slowly exchanging energy and angular momentum. A comet may take millions of years to travel from the distant edge to the region near the core, allowing the consequences of stellar mass loss to appear far later than their original cause. Not every body entering the inner system will collide directly with the white dwarf. Many will simply pass nearby and return to distant orbits. Close encounters with giant planets may redirect them, sometimes ejecting them from the system entirely. Others may approach closely enough for the tidal force of the stellar core to become important. At sufficiently small distances, the difference in gravitational pull between the near and far sides of an asteroid can exceed the internal forces holding it together. The object is then stretched and broken into many fragments. Those pieces do not necessarily fall onto the star at once. They may form a disk of dust and gas orbiting the core. Collisions among the smaller fragments cause them to lose more energy, and the material gradually descends onto the surface of the white dwarf. Through this process, an asteroid that once orbited at a great distance becomes a source of heavy elements in the thin atmosphere of the dead star. This is one of the clearest connections between the surviving orbital structure and what humans are able to observe. When calcium, magnesium, iron, or silicon appears in the spectrum of a white dwarf, those elements cannot remain in the outer atmosphere for long under such powerful gravity. Heavy elements sink rapidly below the surface, so their presence indicates that rocky material fell onto the star relatively recently in astronomical terms. The star becomes a record of the composition of the bodies destroyed around it. A planetary system, after the red giant phase, is neither completely dead nor still functioning as it once did. It enters a state that is more widely dispersed, darker, and slower. The giant planets move along broader orbits, smaller bodies are gradually disturbed, and the white dwarf at the center cools over billions of years. There is no longer a steady source of light sustaining a long-lived habitable zone like the sun does today, but gravity continues to maintain motion and create encounters between objects. A surviving planet will not necessarily retain every moon, and a moon that remains will not preserve the same surface it once had. Icy bodies may partially melt and later freeze again. Atmospheres may be lost, reform, or be stripped away by radiation. Expanded orbits will produce longer years, weaker illumination, and skies increasingly dominated, at first, by a small but intensely hot white dwarf. Soon after the nebula forms, the stellar core may still release powerful ultraviolet radiation, making the nearby environment far from quiet. Over time, that radiation weakens and the region around the white dwarf grows colder. A distant giant planet may continue to exist almost indefinitely by present-day standards, but that does not mean the system will remain completely stable. Very small disturbances, accumulated over billions of years, may still be enough to alter orbits profoundly. Long-term simulations show that systems with several planets may become unstable after extraordinarily long intervals. As one orbit grows more eccentric, a planet may pass close to another, causing one of them to be ejected or transferred onto a new path. For the solar system, The precise outcome will depend on the positions and motions of the planets when the Sun loses its mass, so the future cannot be described as a sequence of events already fixed in every detail. What can be stated more reliably is that two trends will unfold in parallel. Large, distant bodies are more likely to survive, while populations of smaller objects will experience stronger disruption. Expanding orbits will help planets avoid the region near the white dwarf, but shifting resonances may send asteroids and comets into that very region. A system that appears more empty on large scales may continue supplying debris to the small area surrounding the core. If the star that created the Ring Nebula once possessed planets, its system may now be entering a similar stage. The nearest worlds would have disappeared or been transformed as the star expanded. Any outer planets that survived may now orbit farther away around the core that is becoming a white dwarf. At the present distance, they would be too small and too faint to separate easily from the light and structure of the nebula, so the famous image does not yet reveal what remains of the former planetary system. The absence of direct images does not place the question entirely beyond reach. Astronomers have detected planets, dust disks, and rocky material around many other white dwarfs. Each system provides another piece of evidence that planets can survive the old age of their stars, while also showing that the remaining orbits can be disturbed enough to send debris toward the central core. The future of the solar system is not inferred from models alone. Versions of that future have already unfolded throughout the Milky Way. After the nebula's glow fades, the easiest part of an old system to observe may not be an intact giant planet, but tiny chemical traces in the atmosphere of the white dwarf. A single atom of iron or calcium may reveal that rocky material has recently fallen inward. A thin disk of dust may show that an asteroid passed too close. These small signals allow astronomers to study the composition of destroyed worlds from tens or hundreds of light years away. The future Sun may be surrounded by a similar system, outer planets continuing along broad orbits, moons and icy bodies preserving part of their history, and fragments of rock occasionally falling toward the core. There will be no green Earth in its present place and no yellow star dominating the sky, but gravitational motion will continue. The end of the red giant phase will not erase the entire system. It will force the remaining members to find a new balance. This new structure may survive far longer than the ring of gas. The nebula will shine only briefly before merging into space, while the planets and white dwarf continue moving across spans of time, exceeding billions of years. What remains will not be a dim copy of the solar system we know, but a different system built from its former members, with wider orbits, less light, and new pathways carrying matter back toward the core. Those orbits make a special kind of observation possible. When rocky bodies are destroyed and their material falls onto a white dwarf, spectra can reveal compositions that humans previously measured only in planets and asteroids close to Earth. By studying systems that have already passed through the Sun's future, astronomers are learning to read the remains of worlds that are no longer intact, but have not entirely disappeared. Seen from a distance, a white dwarf usually appears as nothing more than a tiny point of light, offering no immediate sign that planets, asteroids, or vast icy regions once surrounded it across billions of kilometers. The nebula has faded, the outer gas has blended into the interstellar medium, and the core slowly cools within what seems to be an empty expanse. Only when its light is separated into a spectrum do the first traces of the former system begin to appear. Calcium, magnesium, iron, silicon, and many other elements commonly associated with rocky material. These heavy elements cannot remain for long in the thin atmosphere of a white dwarf. Powerful gravity pulls them down into deeper layers over a relatively short period by astronomical standards, leaving hydrogen or helium above them. If the spectrum still shows metals, that material was probably deposited recently or is continuing to arrive. The star is no longer producing new elements, so the most plausible source is debris that once orbited around it. In astronomy, the word metal has a broader meaning than it does in everyday language. Nearly every element heavier than hydrogen and helium can be placed in this category. When calcium or iron appears in a white dwarf's atmosphere, it does not necessarily come from a solid mass of pure metal. It may have been contained in rocks, minerals, or material that once formed the crust or deep interior of an asteroid. The proportions of different elements allow researchers to infer what kind of body was destroyed and, in some cases, whether it had once separated into a core and mantle. In the solar system, iron is concentrated in the cores of rocky planets, while silicon, magnesium, and oxygen are common in their mantles and crusts. A body large enough to become hot during formation may separate internally, with heavier material sinking inward and lighter material remaining above it. If debris falling onto a white dwarf contains an unusually high proportion of iron, it may have come from the core of a differentiated object. If calcium and aluminum are more prominent, the material may have originated in the outer rocky layers or in minerals formed at high temperatures. In this way, the spectrum of a dead star can reveal the geology of worlds that no longer remain intact. We cannot see their surfaces, send probes to land on them, or photograph their shapes before they are destroyed. Their chemical composition becomes the readable remnant, like a sample that has fallen on its own into a place hot enough to reveal the signature of each element. The source material usually does not plunge directly from a distant orbit onto the white dwarf in a single event. First, an asteroid or smaller body has its orbit disturbed by surviving planets. Its new path may become more elongated and eccentric, bringing it closer to the stellar core after many revolutions. Once the distance becomes small enough, tidal forces begin to act strongly. The side facing the white dwarf is pulled more strongly than the far side. This difference increases rapidly as the distance shrinks until it exceeds the gravity and material strength holding the body together. The rocky object is stretched and broken into many fragments. Pieces on slightly different orbits continue colliding, grinding one another down and spreading into a disk of debris around the star. This dusty disk is usually far smaller than the protoplanetary disk that once surrounded the young star. It is a compact structure close to the white dwarf, formed after the destruction of one or more smaller bodies. The dust absorbs light from the hot core and remits it in the infrared, producing excess radiation that telescopes can detect. If the white dwarf itself is shining as expected for its surface temperature, but the system gives off additional infrared light, a warm ring of dust is a natural explanation. Not every white dwarf with metals in its atmosphere is accompanied by an easily visible dust disk. The dust may be too thin, too cold, or already mostly consumed. Some debris may turn into gas after collisions and vaporization. Material may also fall inward in separate episodes, leaving chemical traces after the surrounding structure has already faded. Spectroscopy and infrared observations complement one another. One reveals material that has reached the surface, while the other searches for what is still orbiting the core. In some systems, astronomers also observe irregular changes in brightness as debris passes in front of the white dwarf. Instead of one clean dip like the transit of an intact planet, the signal may be distorted, vary in depth, and change from one orbit to the next. Clouds of dust continually reshape themselves, stretch into tails, and block part of the light in an unstable way. Across repeated observations, researchers can follow a body being destroyed almost in real time by astronomical standards. This activity does not begin immediately after the star becomes a white dwarf and then quickly come to an end. Large planets may continue disturbing asteroids and comets for hundreds of millions or billions of years. Even an ancient system can still send material from distant orbits toward the central core. This helps explain why white dwarfs that have been cooling for a long time may still show signs of newly accreted matter. Surviving planets act as agents of rearrangement within the system. In the future solar system, Jupiter, if it remains on its wider orbit, will still have enough gravitational influence to affect countless smaller bodies. A slight disturbance, repeated over many revolutions, can gradually stretch an asteroid's orbit, bringing its closest approach nearer to the white dwarf. In other cases, a planet may eject the body from the system entirely. The same gravitational influence can clear some orbits while supplying debris to the central region. Evidence for surviving planets is not limited to dust and metals. Some planets have been detected directly or indirectly around white dwarfs, demonstrating that the red giant phase does not necessarily erase an entire planetary system. These worlds often occupy wide orbits or have complicated dynamical histories. In some cases, a planet may have formed earlier and survived. In others, its present orbit may be the result of rearrangement after the star lost mass. A planet orbiting a white dwarf does not live beneath the same kind of light that Earth receives today. When first formed, the stellar core is extremely hot, but has a small surface area, and its brightness then declines continuously as it cools. The region where temperatures might permit liquid water also shifts over time. A world at a suitable distance during one period may later become too cold, while intense ultraviolet radiation early on may alter or strip away its atmosphere. Questions about habitability around white dwarfs are still being studied, but they are not necessary to demonstrate the importance of these systems. The existence of planets and rocky material alone is enough to show that planetary structures can outlive the normal active phase of their stars. A system does not disappear at the same moment as its central source of light. It is broken apart, expanded, and carried into new states. Some fragments also contain evidence of water. When oxygen is present, in greater amounts than would be needed to combine with magnesium, silicon, and other rock-forming elements, the excess may suggest that the original material was rich in water or oxygen-bearing compounds. Carbon, nitrogen, and other volatile elements can also help distinguish bodies that formed close to the star from those that came from colder regions. In this way, white dwarfs can reveal not only rock, but sometimes ice and former reservoirs of water within an old planetary system. The data still requires careful interpretation. Oxygen can be contained in many different minerals. Elemental ratios can change when different components fall inward at different rates, and the time of observation affects what remains visible in the atmosphere. Researchers must model both accretion and gravitational settling before estimating how much water a body may once have contained. Even so, the ability to measure the chemistry of material from beyond the solar system in such detail represents a major advance. Ordinary planets around sun-like stars are usually too small and too distant for the spectra of their rocky surfaces to be measured directly. Starlight overwhelms nearly every signal coming from the planet. When a body is destroyed and its material falls onto a white dwarf, those elements appear against a source of light that can be analyzed far more clearly. The destruction has unintentionally transformed a world that was almost impossible to observe into a chemical sample that can be read from afar. Not every system follows the same sequence of events. A white dwarf may no longer have any large planets capable of disturbing asteroid orbits. Another system may lose most of its smaller bodies during the red giant phase. Elsewhere, several planets may survive but remain on orbits so stable that very little material is sent toward the center. The different levels of chemical pollution seen among white dwarfs reflect the diversity of the planetary systems that once surrounded them. That diversity also prevents us from treating any one observed system as a certain copy of the Sun's future. Our system has its own architecture, with 4 rocky planets, 4 giant planets, several belts of material, and countless smaller bodies. The condition of each population billions of years from now will also depend on disturbances that occur before the Sun becomes a white dwarf. Science can identify broad trends, but it cannot yet tell us which individual asteroid will survive, or which object will eventually fall toward the core. What matters more is that such a future no longer exists only in models. The Milky Way already contains white dwarfs with metals in their atmospheres, warm disks of dust, and fragments in the process of breaking apart. These are systems that have already traveled the path the Sun will enter in the distant future. Each one shows a different outcome, yet all confirm that the old age of a star does not erase every trace of its planets. Seen from very far away, one of these systems might not appear remarkable at all. A tiny white point of light rests among the stars, with no brilliant ring of gas and no planets that can easily be seen. Only sufficiently sensitive instruments can detect excess infrared radiation or the absorption lines of metals in its spectrum. Those delicate signals contain an entire history. The star once swelled, the orbits expanded, large planets continued pulling smaller bodies away from their former paths, and an asteroid passed too close and was torn into dust. A similar story may one day unfold around the white core left by the Sunday Jupiter, or the outer planets may disturb surviving fragments of rock and send some of them onto elongated orbits. One body may approach the white dwarf, break apart, and form a thin ring of dust. Some of that material may fall into the atmosphere, where iron, silicon, or calcium leaves spectral lines for any distant observer with instruments sensitive enough to detect them. Those observers may never know that the system once contained a planet with oceans, continents, and living beings looking up at the sky. What remains readable may be only the composition of rocks, the proportions of different elements, and the structure of a few wide orbits. Most of the detailed history will have been lost, yet matter will still preserve a layer of memory of its own. A calcium atom in the atmosphere of the white dwarf could be the final remnant of a body that orbited the Sun for billions of years. The Ring Nebula is still at an earlier stage, when the glowing gas conceals much of the story of any planetary system that may once have surrounded the central star. If distant outer planets remain, they are not easy to detect through the immense distance and the nebula's complicated structure. Once the ring fades, future observations may search for dust, metals, or surviving worlds around the core. For now, other white dwarfs provide the evidence that this particular object cannot yet reveal clearly on its own. Through those systems, the phrase, "what remains," comes to mean more than a small star slowly cooling. The remnants also include planets on new orbits, moons separated from their former worlds, comets ejected into interstellar space, asteroids ground into dust, and heavy elements gradually sinking beneath the surface of the core. The planetary system is still active, but its motions have become slower and more widely scattered, no longer organized around a steady source of light. This is also where the comparison with the Sun's future becomes clearer while requiring even greater care. The Ring Nebula reveals the general mechanism of losing the outer layers and forming a white dwarf. Polluted white dwarf systems show that planets and debris can continue to survive. No single object provides the entire picture. Instead, we combine many systems at different stages to construct a future grounded in scientific evidence. That picture is not an empty ending. It is a transformation from a bright, stable system into a darker one that still remains in motion, where what once formed planets may become a source of information for astronomers far away. The old worlds may no longer remain intact, but their material has not vanished, and the orbits of surviving planets continue to carry the history of the star that created the system. This evidence brings the story back to the original question. The Ring Nebula shows us many accurate outlines of the Sun's future, but the ring itself is only one of countless possible outcomes when a star grows old. The general mechanism can be predicted with considerable confidence, while the shape, brightness, and detailed fate of each planet still depend on the system's individual history. To understand how closely the ring resembles the future of the Sun, we must clearly separate what is nearly certain from the features that belong only to the star now resting within the constellation, Lyra. Text. After exploring the three-dimensional structure of the ring, the light from the stellar core, the molecular gas clumps, the outer arcs, and the traces of planetary systems around white dwarfs, the original question can now be reconsidered with greater clarity. The object in the constellation Lyra truly does allow us to observe one kind of future awaiting the sun, but not in the sense that every color, outline, and detail in the image will one day be repeated around our own star. The similarity lies in the broad path of stellar evolution. The differences lie in how each star travels along that path. The most certain part of the story begins with the sun as it is today. It is a low to intermediate mass star, fusing hydrogen in its core, and it is not massive enough to end through the collapse that forms a neutron star. As hydrogen in the central region declines, the core will contract, the burning region will shift outward, and the atmosphere will expand. The sun will become a red giant, gradually lose material through powerful stellar winds, and eventually expose a hot core composed mainly of carbon and oxygen. That core will ultimately stabilize as a white dwarf. This sequence of changes is supported by many layers of evidence: physical models of stellar interiors, observations of star clusters at different ages, spectra of red giants, expanding planetary nebulae, and the large population of white dwarfs throughout the Milky Way. No telescope has followed a single star through billions of years, but the individual stages can be seen at the same time in different stars. When those pieces are assembled, the sun's general evolutionary path becomes quite secure. The star that created the Ring Nebula also passed through similar stages. It remained stable through most of its life, entered a giant phase, lost its atmosphere, and left behind a hot core now moving toward the white dwarf state. At this level, the object truly is a window into the sun's distant future. The glowing gas shows that material once belonging to a star can expand into space. The point of light at the center reveals how small the remaining core can become. The entire structure demonstrates that the ending of a sun-like star does not require a supernova explosion. Yet the same evolutionary path does not produce the same scene. The original central star of the Ring Nebula was probably more massive than the sun, although it still belonged to the class of stars that do not end in core collapse. A difference in mass affects nearly every late stage: the rate at which fuel is consumed, the temperature of the core, the amount of material lost, the time required for the core to heat up, and the brightness of the gas after it becomes ionized. Even a relatively small difference in initial mass can produce a nebula that is brighter, lasts longer, or has a different chemical composition. The future sun will probably produce a planetary nebula, but it may not be as prominent as the example we observe today. For the gas to glow clearly, the core must heat up quickly enough before the outer material expands too far. If the cloud has already become significantly thinner, ultraviolet radiation may still ionize part of it, but the total light emitted will be weaker. The sun lies near the lower mass boundary of stars capable of producing an easily visible planetary nebula, so the result may be fainter and shorter-lived than the famous ring. Its shape is even more difficult to predict. A nearly spherical shell of gas can appear as a bright circle when more light accumulates along its edge. Dense material around the equatorial region may produce a distinct band, while faster outflows along the poles may create an elongated structure. Rotation, magnetic fields, convection cells, and uneven episodes of mass loss can all leave their marks. The viewing angle from a distant star system will then determine whether the three-dimensional structure appears as a ring, an oval, two lobes, or a nearly circular cloud. No viewing position can be regarded as revealing the one correct shape. Astronomical images are always projections of objects onto a two-dimensional sky. A nebula that resembles a ring from one direction may appear elongated or divided in two from another. Even if the sun creates a relatively clear band of gas, observers elsewhere in the Milky Way may not see anything resembling the ring in Lyra. The underlying physics may be similar, while the visible appearance is entirely different. The possible presence of a companion star around the Ring Nebula's central remnant makes the comparison even more uncertain. The fairly regular spacing of the outer arcs suggests that a low-mass object may once have shaped the outflow according to its orbital cycle. If this hypothesis is correct, the present structure is not the product of an isolated star. It was formed through the motion of at least two objects, with the companion's gravity imprinting a rhythm on the expanding gas. The Sun has no known stellar companion in a similar wide orbit. The planets, including Jupiter, can influence the motions of smaller bodies and the overall center of the system, but their masses are far too low to act like a small star in shaping the released atmosphere. If a companion was important in producing the thick ring and the outer arcs, the Sun's future nebula will lack that particular mechanism. This does not mean the Sun is certain to create a simple, spherical shell. Even a solitary star rotates, produces magnetic fields, pulsates, and has an uneven convective surface. The giant planets may exert slight influences on the surrounding environment during certain stages, although the strength of those effects remains a subject of study. The final structure may still contain rings, filaments, or asymmetrical layers, but there is not enough evidence to draw a complete ring in advance with every known feature already in place. The fates of the planets are also similar only in their broadest trends. Mercury and Venus will almost certainly not survive the red giant phase intact. Earth will lose the conditions needed to support life long before the outer gas expands toward the region of its present orbit. Whether the remaining rocky body is completely engulfed by the Sun or narrowly avoids its outer edge will still depend on the rate of mass loss, the expansion of the orbit, and tidal forces in future models. The outer planets are more likely to survive and then move into wider orbits as the Sun loses material. The same general response may have occurred around the star that formed the nebula. If distant planets once existed there, they may still orbit the core at new distances, too small and faint to be easily detected in present observations. The similarity does not require each planet to have a counterpart. It lies in the general response of planetary orbits to the declining mass of the central star. There is no way to know whether the planetary system that once surrounded the Ring Nebula resembled the solar system. It may have contained large gas planets, rocky inner worlds, or no significant planets at all. Even if planets were present, their own dynamical history would determine which bodies were ejected, which moved close to the core, and which continued to survive over long periods. The glowing gas does not preserve a complete inventory of the former worlds. Chemical composition creates further differences. The amounts of carbon, oxygen, nitrogen, and dust in the gas depend on the star's original material and on the mixing processes that occurred inside it. Two nebulae formed by stars of similar mass may shine differently because their elemental proportions are not the same. The colors in astronomical images also depend on the filters used, the way the data is processed, and the state of ionization, so saying that the future Sun will produce the same bands of color would have little physical meaning. The time of observation matters just as much. A planetary nebula changes as its gas expands and its core cools. An earlier view may reveal a small, dense, bright shell. A few thousand years later, the same object will be larger and thinner, with more recombining regions and less distinct boundaries. The present image captures only one stage within an ongoing process, not the permanent shape of the remnant. If a distant observer were watching the future solar system, what they saw would depend on when the light reached them. They might see a dusty red giant, a newly exposed hot core inside gas that had not yet become fully ionized, a faint expanding nebula, or a white dwarf whose cloud had already disappeared. The statement, "This is the future of the Sun," is accurate only when tied to a particular interval within the long sequence of change. This limitation makes the comparison more scientific, not less compelling. The Ring Nebula does not need to be an exact duplicate to help us understand the future. It shows how nuclear physics, gravity, and radiation can transform a stable star into a small core surrounded by glowing gas. Individual features, such as the number of gas knots, the thickness of the band, the rhythm of the arcs, or the particular colors, belong to the unique history of that system. What we know can be divided into three levels. With high confidence, the Sun will become a red giant lose its outer layers, and leave behind a white dwarf. With strong support, but some dependence on models, it may produce a relatively faint planetary nebula for a short period. What cannot yet be predicted precisely includes its shape, brightness, small-scale structure, the timing of each gaseous layer, and the final fate of certain individual bodies. The Ring Nebula is glowing at a very particular moment in its life. The layers of gas that once belonged to the star are still close enough and dense enough to receive energy from the hot core at the center. Hydrogen, oxygen, and many other elements continue to emit light, creating a luminous band visible from thousands of light years away. But this state will not last forever. With each passing year, the cloud expands a little farther, its material spreads across a wider region, and the distances between its atoms continue to grow. The ring will not suddenly go dark like a lamp being switched off. Its light will fade slowly as two processes unfold together. The gas will become too thin to glow strongly, while the stellar core begins to lose the heat it still retains. Ultraviolet radiation will no longer maintain ionization across as wide a region as before. Atoms will recombine more often, and the once prominent outlines will begin blending into the faint halo around them. The dense clumps of gas will not preserve their shapes either. The sides facing the core will continue to be eroded by radiation, while material escapes from each knot and mixes into the thinner surroundings. Their elongated shadows will change as the central source grows weaker and the structures in front of them are worn away. The arcs along the outer edge will continue moving farther outward until their spacing still exists physically. But they no longer produce enough light for telescopes to detect easily. Over several tens of thousands of years, the planetary nebula will gradually lose its distinct boundaries. Its gas will not disappear. The atoms will simply spread into the interstellar medium, where matter is already extremely sparse. The glowing ring that once carried its own name will become part of the Milky Way, no longer easily separated from the other clouds drifting between star systems. At the center, the white dwarf will continue along a path lasting far longer. It no longer has an immense atmosphere, no longer sustains stable nuclear reactions, and can never return to its former stellar state. The heat stored within the core will be released little by little into space. Across the billions of years that follow, that point of light will slowly cool while any surviving planets or debris continue along their rearranged orbits. One day in the distant future, the scene once known as the Ring Nebula will exist only in light that left it long before. Observers at different distances will see different moments in its disappearance. From a nearer world, the ring may already have faded. Farther away, its older light will still be traveling through space, carrying an image of the nebula from the time when it remained bright and distinct. In the universe, an object may already have changed, while an earlier version of it continues spreading outward in the form of light. The story of the sun will pass through a similar transformation, although its final shape will not necessarily resemble the ring in Lyra. Today, sunlight still crosses the distances between the planets, warms Earth's surface, and supports the familiar rhythms of life. Deep within the core, hydrogen is still being converted into helium. The balance that has sustained the star for billions of years remains secure, and its final changes lie so far away that they belong to no near future of humanity. When we place a hand in sunlight today, there is no sign that this source of light will one day become a red giant and then contract into a core roughly the size of Earth. The present light does not seem old or carry any warning of an approaching end. It is simply the light of a star in the middle of its stable lifetime, continuing what it had been doing long before human beings appeared. It is this very ordinariness that makes looking at a planetary nebula so remarkable. We do not need to wait for the sun to change in order to understand what awaits it. The Milky Way has placed stars at many different stages around us. Some are newly forming, some are living stable lives, some have swollen into giants, and others have left behind only expanding gas around a hot core. Each object provides one part of a story longer than any individual life could ever follow. The Ring Nebula is not a warning sent to Earth, nor is it an exact image of the day the sun reaches its end. Its value lies in making an unimaginably distant process observable. Within that glowing band, we see the atmosphere of a star that has left its former place. In the point of light at the center, we see the small but dense core that will remain after the cloud has dispersed. In the faint arcs and dense clumps, we see that the final history of a star does not unfold evenly or simply. What remains after a star is not a single object. There is a core continuing to cool, gas spreading into the galaxy, dust and elements being returned to space, and perhaps planets moving along new orbits. Some bodies may survive almost intact, while others are pushed farther away or broken into debris. Matter that once belonged to the same system no longer remains together as before, but it continues taking part in other motions throughout the galaxy. The released gas may mix with clouds between the stars. After an immense amount of time, some of that material may enter a region where new stars are forming. Carbon, that once lay in the outer layers of an aging star, may become part of the dust around a young system. Oxygen that once glowed within a nebula may become a component of rock, ice, or gas on a world that does not yet exist. No individual atom is guaranteed to follow any particular path, but across the galaxy, matter is reused through many generations of stars. The sun and its planets were also formed from material with a history that began long before the solar system. Many of the elements found in Earth, in the oceans, and in the human body were once created or dispersed by stars that lived before us. A fading planetary nebula does not merely mark the end of a stellar life. It also returns to the galaxy materials that may later become part of structures still waiting to form. This does not mean the universe moves through a perfect circle. Matter is reused, but every system forms under different conditions, with its own mass, composition, and environment. No star returns in exactly the same form, and no planet is a complete repetition of a world that has disappeared. The continuity lies in the material and the laws that govern it, while every structure retains a history that can never be precisely repeated. When the light of the ring enters a telescope, it allows us to stand between two directions in time. We are looking into the past of a star thousands of light years away, while using that past to understand the future of the nearest star to us. Ahead lies a stage the sun has not yet reached. Behind lies a process that has already unfolded somewhere else. The two meet within the photons collected here on Earth. In the end, what the Ring Nebula reveals is not a final day, but the way a star changes when it can no longer preserve the structure that sustained it through most of its life. It expands, releases material, briefly illuminates its former atmosphere, and leaves behind a hot core. The planets around it enter new orbits and new conditions, while gas that once belonged to the star returns to the wider galaxy. The sun is still very far from that moment. Beyond the window, its light continues to pass through the atmosphere and spread across rooftops, water, and familiar ground. The nebula in Lyra remains so distant that it cannot be seen with the naked eye, yet between these two sources of light exists a connection deeper than distance. One star is still in the middle of its life, while the other has left behind the traces of its ending. The ring will eventually fade. The sun will eventually change. Familiar forms do not last forever, but their matter and light continue traveling outward, carrying their histories to places they have never reached before. Within that slow movement, the future does not arrive as a sudden emptiness, but as a new state formed from everything that came before. And as the room grows quieter, the sun continues to shine from a little more than 8 light minutes away, while the Ring Nebula continues sending Earth the image of a star that changed long ago. One light belongs to the present, another arrives from the past, and between them lies the story of the distant future of the star that has accompanied every day this world has ever known.